Now, the question came up before I turned on the recorder, so let me repeat the answer to this. The question was about attendance. Uh, your grade in this course comes from your performance on your labs, your performance on your tests, and your research paper. Research paper counts as a test grade. Um, you, there will be a final at the end. The research paper and the final cannot be dropped. One of your chapter test grades could be dropped. Your lowest score could be dropped if that helps your average. Okay, we're going to have labs after every chapter. We've been having them so far. We're going to continue having them. It looks like we wind up with 9 labs, so I'll drop your lowest lab score. Okay, that gives you 8 labs that you'll be averaged together. They're all based on 25 points, so that'll give you a value something between 0 and 25 points. Hopefully most of you near the 25 points. Okay, then your test scores and your research paper and the final exam, they will, whatever you get on that, I'll take 75% of that, add it to your lab score. That gives you your final grade. You're graded on your performance, what you turn in. Okay, the attendance, though, they require that we take attendance. Now, someone said some of their other instructors don't. That's fine if they choose not to, and that's okay with everybody. It's fine. I've been told, put attendance on Blackboard. So I do. It's an awkward system, but I've figured out how to do it last week with some help, and so I've started doing that. So your attendance is out there. The only time that will come into the picture is at the end of the term if you happen to be right on the borderline between an A and a B or a B and a C or something like that, but not quite enough to go up. If you've had really good attendance that all term, that may be enough to bump you up a fraction of a point, to give you a B rather than a C, to give you an A rather than a B. Maybe, hopefully you're not there, but to give you a C rather than a D, okay? But hopefully you're not down there. So, but your grade depends on your performance. The attendance can maybe add a fraction of a point at the end of the term. Usually for most of you, that's not going to change your letter grade at all. It's only for people who are right on the cusp, and that it can bump you up or leave you right where you are, depending on where that is. All right, so I said that again, mostly for people who aren't here. Okay, now let's talk about any other questions or issues or concerns before we move any further. That was an excellent question. It was enlightening to me to know that some people sound like they're not doing attendance. I was led to believe we had to. So, but everything is new this term. The new operating system, the new requirement that we have this template in Blackboard that's really awkward and takes a lot of time and doesn't give you any more information. In fact, it tends to bury the information in my mind. So, but anyway, in this course, you're going to have something to turn in every week, okay? If you think about it, we've had 3 labs, 3 tests. Today we're going to have a 4th lab. I'll give you your 4th test, and we're only in week 4. So that's 8 pieces of information coming in. You're having stuff every week. So basically, you turn in stuff every week. Now you always have a week to work on it, so the stuff that we do today is not due until next week, but get it in. Okay? Any questions? All right, let's talk about where we are and where we're going. We're in chapter 18, plate tectonics, and let me, while we're here, go and get the PowerPoint started. I'm going to open up both 18 and 19 because I think we have a shot at getting into 19 before the day's over. PowerPoint's taking a long time to load. Okay. Yes. Right. Okay. That sounds like a winning combination there. Anything you do miss, I am recording. That'll be loaded. I can't swear it'll be loaded by the end of the day today. Sometimes it is finished by the end. Other times it's not. Most of the time, especially if I'm here until close to 10 o'clock, it does get loaded. Oh, here comes Brianna. Let me get her in. Okay. Brianna's here. And um, so even if you were to miss part of the lab, you'll be able to pick that up. In fact, today's lab is something that I think most of you are probably going to choose to do on your own, but I'm going to be available if you have questions. Okay. So let me see if I can find where we were. Yeah, here we are. Okay. So let me go back to Zoom. Okay. And pull up the chapter 18. All right. So, yeah. So if you do have to miss for some, and I know that life gets in the way, okay, then don't sweat it. Be here as much as possible. That's why I record the classes. That's why we have it out there. Okay. So by all means, get done what you need to do, but be sure you get done for me what you need to do, because your grade depends on that. Now, before I do much else, I've got to do some housekeeping here. They have this toolbar. I assume it's a Zoom toolbar, and I try to move it so it gets out of the way so I can read the PowerPoints. Doesn't get in your way, but it does mine. All right, and we are going to see if I can find the place we left off last time. I think, why is that not showing? I think we talked about that slide. Y'all can see my slides, right? I believe seismic waves is where we were going to pick up this time. I think we started talking about this, but did not finish the slide. Is that where y'all remember? Okay, so let's go from that current slide. Can everyone see it now? Yes? Anybody? I hope you can, right? All right. Well, I would figure if some of you couldn't see it, you would be yelling, no, I can't see that. Okay. Seismic waves. And I think we started this slide. We got most of it done, but let's just catch and review. 3 types of waves. Okay. The first of these is the P wave. And that P probably stands for primary wave. But you can also think of it as a pressure wave, compressional wave, pressure wave. Another name for it is a longitudinal wave. All 3 of those will work. Primary wave, compressional wave, longitudinal wave. These are the fastest wave. Okay, let's stop and talk about what we mean by longitudinal. Now, I think we did this last time, but just as a review, if indeed you had a spring that could hang around like this, most of the time they're going to sag in the middle, so this is a very special spring, okay? And if you were to give it a sudden push to the right and compress the coils here, and then yank it back to the left and what we call rarefact the coils, pull them further apart, here you have a pressure wave, okay? The particle motion was right to left, okay? The wave goes right to left, horizontal, you might say, longitudinally, in the same direction as the particle motion. A little bit later, you'll see the compression here. They didn't draw this well. The compression would show up here, the rarefaction there. The wave is moving in the same direction as your displacement, okay? That's what makes it a longitudinal wave. You compress it and rarefact, that's what makes it a pressure wave or compressional wave. P wave, what makes it primary, it's the fastest, okay? Now, I think I was starting to say this before. if you were to put your hand in front of your face when you're talking, you'll feel little puffs of air hitting your palm. That's a pressure wave. Pressure waves move out in the same direction of that compression and rarefaction. Compression and rarefaction. A little bit later, now the compressed area is down here, the rarefied area is here. If you had started another one, it would be coming down. That's a pressure wave. Primary wave, the wave propagation is in the same direction as the particle motion. Okay. The S waves, and again, S could stand for a couple of things here. In fact, maybe even three here. Secondary wave, okay, S. Shear wave, S, or second fastest, which is really secondary. So it's really just two. Okay, this is the second fastest wave. Now here's the difference in an S wave, a shear wave. Now the other name for it, just like this one had longitudinal, this one has transverse. Trans means against, and verse means sort of like which way the thing's heading. And a shear wave, shear means perpendicular to. So here's what's happening. And I don't remember if I started this story or not last time, but when I was a young kid and we were doing something either in the yard or in the garden or somewhere like this, and my folks had a hose stretched across the ground, whatever we were doing, and they weren't using it, okay, at the time, I loved to get the end of that hose and jerk it up as high as I could and whip it down as fast as I could. And what happened, you see that little hump moving down the hose. I would do it as hard and fast as I can to see how far down the hose I could do it. Well, guess what? That was a shear wave, a transverse wave, because my motion was up and down, but the wave propagation was horizontal. I was up and down, it was horizontal. That's a transverse or a shear wave. They don't move as fast as a primary wave. So here's the example of that. You're holding here, you move your hand up and down, and yet the wave moves in the same direction as the compressional wave did. Doesn't move as fast, but it does move. Okay? Now, I skipped the third point on the P wave. The P waves move through solids like rock, interior solid materials, but also through liquids. And I think I started saying this again. If you've ever been in a swimming pool and gotten underwater, you'll notice that you hear things very distinctly underwater. And that's because remember, sound is a pressure wave. They go through liquids. Okay. Whoa, somebody just came in. I just can't see who it is. Let me hold on. Ah, that's Diana. Let me get Diana in the room. She didn't come in. She asked to come in. But this something about Zoom here, it blacks it out, when it says someone's coming in. And that makes it really hard to see who it is. So Diana is coming in if she's not here already. So this should give us, let's see how many. 10 students. Let's see if we got them. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Got them. Okay. It's shaping up to be a better size class. I was afraid at the beginning it was going to be pretty low attendance, but I'm glad y'all are coming. Now, so P waves, pressure waves, longitudinal waves will either move through solids or through liquids. Okay. In fact, I don't even like to use the word liquids. I would say fluids. Okay. You might say, hey, isn't that the same? No, gases are also fluids. Okay. You don't have to be a liquid to be a fluid. Okay. Fluid could be either a liquid or a gas, and P waves will go through solids and fluids. S waves, however, only go through solids. They do not travel through liquids. Okay. Now, the other issue, now this isn't really pertaining to anything on the slide, but just as a reminder, I think I started this story too. If you ever watch the old Western television shows or movies and those kinds of things, where you either had the cowboys and the Indians or the cowboys and the bad guys. It was usually the sheriffs or the good guys and the bad guys or whatever. When you had those two groups, sometimes either the crooks were trying to rob the trains or the Indians were trying to determine whether it was safe to move the buffalo herd across the tracks or not. But how could they tell when the train was coming? Well, if you listen in the air, the fluid, you could hear the train coming, but not from very far away. It would take a long time. They would be pretty close before you heard them. However, when they put their ear against the track, the metal track, they would hear the train way, way further away because the solids actually transmitted the sound better than the liquids did, just like the liquid transfers it better than the gases do. So again, that's because they're pressure waves. Secondary waves don't go through liquids or gases. They only go through, now, transverse. There's going to be an exception to this, and I'll talk about that coming up. Don't sweat it now, but we'll talk about it. The third type of seismic wave is the up and down crest or trough wave that are only on the surfaces. Now, they say they're much like water waves, okay? If the water's sitting there very still and you throw a pebble into it or a rock or something like this, then you see the up and down motion move out from wherever that point of contact was and head out into the distance, okay? That sounds a lot like a S wave because it's up and down, but it's slightly different, okay? These are only on the surfaces. The S waves go through solids, through the earth. Surface waves only travel on the surface of the earth. Now, I don't know if you've ever seen a picture, when they've taken a video shot of, say, a big explosion going off, like when they're blowing up a building, or like an atomic weapon, when they've shown the pictures and the movies of that. What you'll notice is where the explosion happens, you start seeing a ripple effect going out. It could be in the soil, it could be in the dust, it could be in a liquid. It moves out just like that rock going into the water. Those are up and down, crest and trough waves, surface waves. They're much like the water waves, they're the slowest of these three, okay? However, some of the things we'll see show they may be the biggest of the three, okay? Now, what the surface wave is when a primary wave or a secondary wave reaches the surface. Because remember, the P waves, we're talking about seismic waves, waves that are produced when there's an earthquake, okay? And when there's an earthquake, it always occurs inside the earth. Earthquakes don't typically occur on the surface. You feel them on the surface. They occur way down deep. And we'll talk about how far down deep later, okay? But when that pressure wave makes its way to the surface from way down deep, when it reaches the surface, see, the pressure wave's going like this. When it reaches the surface, it does a surface wave. Same thing with the secondary wave. It goes like this till it reaches the surface, and then it produces and here's somebody else coming in. I can't see who it is. I really can't let them in. Well, let's see if I can see them this way. James is coming. So let's see if I can get him in. Okay, here comes James. The cook is here. Okay, we can all eat again. Okay, whoops, I'm upside down. All right, James is here. And that gives us 11 students. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Got it. Okay. Now, so let me minimize this. Okay, so either the pressure wave or the secondary wave, the P wave or the S wave, coming through the earth, when they reach the surface, then that's where you have the surface waves. That's what shakes buildings, and things. The surface waves do. The P waves and S waves, they're still inside the earth. So this is really what we see as doing the damage, and that's why I said sometimes they are the biggest waves, even though they're the slowest waves. They don't move as fast as the P or S. Okay. Now, why are we even mentioning that? Well, because I can't get my... Okay, here we go. Here's what they're going to do. They stop right there. Okay? And then they start talking about the Earth's internal structure. Okay? This is over on page 460. Okay? There are a few more things here in our text that weren't mentioned on the slides. Not a big deal here, but just in case you run into this. There are two types of surface waves. One is called the Love waves, named after A.E.H. Love, who created formulas to describe them. The Love waves are horizontal waves that move side to side, and that motion is the one that knocks buildings off their foundation, can destroy bridges, highway overpasses, that kind of thing. The second of these is a Rayleigh wave. They're more like the rolling water waves. The Rayleigh waves are more destructive because they produce more up and down and sideways movement for a longer time, and they're so often known as ground roll. Okay, so don't sweat that, but I did want to mention it because there's two more potential names and things that you could write about, so I wanted to mention those. Notice I'm always talking about these papers, okay, because that's a test grade that cannot be dropped. So please, folks, don't forget about your research paper. All right, now we're coming back to those seismic waves later, okay? Very important, but they had to get the background of those done, and now talk about Earth's internal structure, and then we're going to mix the two together, and you'll see how they connect. So let's talk about Earth's internal structure. This begins pretty much on page 461, or if you have the little books, 18-4, the fourth page in chapter 18. Oh, time out again. I started on this. I think there were questions, or I got to talk about something else. Let's go a quick review of what we're doing now. We're in chapter 18. We're going to continue in chapter 18. We may or may not finish chapter 18 today. It doesn't matter because we're going to stop at 3:45 and do the chapter 17 lab. I put it out there on I may have put it last week and this week, I don't remember, but it's out there. I know it's on this week 4 lab. Okay, it's there. If you haven't already printed it, or however you want to do it, it's there and you can look at it. Several of you have been turning in just typed out or written out answers. That's fine too. This one's got a lot of blanks on it, as you'll see when we get there. The last 2 hours we're going to be, I'll give you that time to do the lab. And like I said earlier, before some of you came in, you're probably going to choose to do this on your own, okay? But I'll go over it, we'll get started in it, and I'll give you all the things you need for it. I'll stay online as long as you want me to, but I imagine at some point you're going to want me to get out of your way, shut up, so you can get to thinking about what you're doing and do the lab on your own, because it's a strictly computer lab. You'll go to not just one website. One website's going to give you most of the information you need. You'll probably need to do a few other things to get the information you need, and you fill out the lab. Okay? But I'll stay on as long as you have questions, and then when you finally say, hey, that's it, leave us alone, let us do it, then I'll check out and go on from there. And then at that point, sometime after that, I'll put your fourth test out there. I don't think I put that out there on Blackboard Message yet, but I'll do it. Sometime in the future, if I can figure out how to do it, I may start putting it under your weekly assignment rather than on Blackboard Message. But since I've already started on Blackboard Message, I think I'll just continue doing that because that's where y'all are used to looking, so that's where I'll say do it. All right, so let's look at Earth's internal structure. Three main zones, okay? The very, very outer bit, okay, is a thin, thin outer shell, is called the crust. Everything you see, and basically just about everything we've ever entered, has been the crust. Even the deep mining that has been done, we've stayed within the crust. There are a few places where the mantle that we're going to talk about next actually approaches the crust, and I guess you could say we've been into the mantle where that happened. But very seldom are we going to drill down far enough to get into the crust, into the mantle. We're always in the crust. The deepest mines that you'll ever find basically are still in the crust. The crust can be up to so many miles thick. We don't typically go down miles into the crust. We just don't do it. Okay? But it's very thin compared. Now, miles doesn't sound like it's very thin to me, but when you consider how big the Earth is, just a few miles is a tiny, tiny fraction of how big the Earth is. So it's a thin outer shell. After that, you have the mantle. Much, much thicker than the crust. The crust like this, the mantle much thicker. Okay? And then you get down to the inner part, and that's called the core, the very central part of the Earth. And the core actually has two parts. We'll get to that a little bit later too. And that's where the seismic waves come into play, believe it or not. All right, so here's a picture of it. This very thin, thin little layer out here, remembering that can be miles thick, but that's still the crust, okay? Still the crust. Then the mantle goes from inside it all the way to the edge of the core. That is the biggest part of the Earth. Now, they're showing two different colors here for the mantle. There is a reason for that, okay? This is called the upper mantle up here, the lower mantle here. And we'll talk about this line in between. We'll also talk about the line between the crust and the upper mantle. There's also a line between the upper mantle and lower mantle. Then there's also an outer core here and an inner core there. And there's a difference here. We'll get to that. The core is everything inside the mantle, outer and inner. The mantle is what's between the core and the crust, upper and lower mantle, and then the crust is the crust. There's actually two types of crust. We'll get into that as well. Okay, so let's move on. Any questions on the Earth's internal structure? Very good illustration here. I'll tell you a few things that are faulty about this illustration. This looks like everything is a nice smooth boundary. It's not. It's rugged, it's jagged, it protrudes, okay. It's not nice and smooth like this. Neither is this one here. That's not a nice smooth boundary between the upper mantle and lower mantle. It's jagged, it's ragged, it protrudes, it does all sorts of stuff. This is not a nice smooth boundary here between the mantle and the outer core. No way. It's ragged, it's jagged, it's rough, there's a lot going on there. And even between the inner core and the outer core, though nobody's been down there to see, they haven't even seen this, they haven't even seen that, I guarantee you though, they're not nice and smooth. They are uneven, irregular, ragged and jagged. Okay, so that's what's wrong with the picture. The picture's good illustration of the concept, but don't think they're nice, smooth boundaries like that. They hardly ever are. All right, so let's start with the crust. The crust covers the entire Earth. Again, not very thick, just a number of miles thick, okay? In fact, different crusts have different thickness. This will be our next lab, our Chapter 18 lab, will be looking into this. The oceanic crust, now remember, you got the oceans that go miles deep, and then you have the oceanic crust underneath the water. And generally, these are much, much thinner than the continental crust. They're mostly made out of basaltic rock. Now remember that from the last chapter? Last chapter, the basalts were dark, meaning high iron content. That means they're very dense because of the high iron content. They're very fine grained because they cool rather quickly. They come from volcanic sources, just about uniquely. Okay, they're dense, thin crust. And again, when I say thin, maybe miles thick, but not that many miles. Then the continental crust, that would be what's under us now, what's under most of us. It's mostly, not totally, granite rock. Okay? Remember, granite was a light colored but also light density rock. Light colored and light density because it doesn't have much iron in it, whereas basalts have, they're dark, they're dense. A lot of iron, very little iron in granite, so they're less dense. But they're much thicker than the oceanic crust. We'll see an illustration of that coming up. In fact, let's do it now. So, somewhere down here is the mantle. Understand this can be miles thick here, miles and miles thick here. Okay, here you have your water over the oceanic crust, and the mantle is somewhere down here. Now this picture is much more realistic in the fact that the boundaries here are definitely not smooth and rounded. They are ragged and jagged. There is one fault I find with this picture. We'll talk about this later. The oceanic crust, because it's denser, very seldom will climb up the continental crust. It will subject under the continental crust because it's denser. It's not as dense as the mantle. The mantle is, again, mostly iron, but higher concentration of iron than the basalts on the ocean crust. But that's the problem with this picture. This crust here, rather than climbing up over the continental crust, should be subducting down under it. That would be more precise. What they show here is the same volume of oceanic crust is going to weigh more than the same volume of continental crust because it's denser. More mass per unit volume. Okay? That's what this is saying. Equal masses, this will be much denser. And that's why it subducts under rather than crawling up over. Okay, so those are those illustrations. Again, miles thick here, more miles thick here. We'll do this in the next lab. Not today's lab, Thursday's lab. Then you have what they call, boy, this is a tough one to pronounce. I've never heard it pronounced, so I'm just guessing. Mohorovičić, I think is how you say that. Words that end in this usually have a CH sound here. Mohorovičić discontinuity. That's the discontinuity between the crust and the mantle. So this would be that Mohorovičić discontinuity. Now, quite often they'll abbreviate it and just call it the MOHO. Okay, the MOHO. It's a lot easier to say, but that's the discontinuity between them. Even between the oceanic and the mantle, both high iron concentrations, these are denser, those are less dense. These are denser than those, but they're less dense than these. There is a discontinuity here between the mantle and either one of the crusts, and that's the Mohorovičić discontinuity. The mantle crust boundary, and that's the, we know that's there because the seismic wave velocity increases sharply from crust to mantle. Now again, this statement is a little bizarre because most of your seismic waves start in the mantle and go to the crust. They don't go start in the crust and go to the mantle. However, some do. Okay, some do, but most of them go from mantle to crust. So then I would have said the seismic wave velocity decreases sharply when it goes from mantle to crust. That would have been a little more precise, but it's true both ways. It is true both ways. Now, again, let's go back to the previous picture. This is then the MOHO, or Mohorovičić discontinuity. And you see, whereas they show here the crust being nice and even, it's not. Continental crust is thicker, oceanic crust is thinner, so this should be quite thin right here. This should be quite thick right here, okay, because that's under a continent. But they don't show it that way. And it's not nice and smooth. It's a lot closer to what this is. Really ragged and jagged, broken and uneven. But the difference, the boundary there is the Mohorovicic discontinuity. All right, that's the crust. Let's move to the mantle. When they say a thick shell between the crust and the core, they mean a thick shell. Okay, going back here and looking, that thickness here, way thicker than the crust by long shots, but even thicker than the core. This core probably is exaggerated just so you see it better. The mantle, remember this is also mantle, that's mantle, this is upper mantle, lower mantle, we'll get to that later. That's much thicker than this, and way thicker than the crust. Okay, so thick shell between the crust and the core. It takes up 80% of the Earth's volume. Okay, 80%. Okay, it accounts for 2/3 of the Earth's mass. That's only 67% of the Earth's mass. Why is that? Because the core is much denser than the mantle. The mantle is much denser than the crust, but the core is much denser than the mantle. Why? You have all that gravitational attraction adding and pushing the molecules of the core even closer together than those in the mantle. Okay? So while it takes up 80% of the Earth's volume, only about 67% or 2/3 of the Earth's mass. It's composed mainly of olivine. Now, if you remember olivine, that was the one that came out of magma solution at the highest temperatures. Way down, that will come out of solution. That's olivine. Okay? A ferromagnesium silicate. Still got silica in it, but heavier on the iron and magnesium than it is on silicon and oxygen. Still has oxygen down there. Remember, oxygen is everywhere. Okay, not as gaseous oxygen, but as solid molecular oxygen. Okay, we have very seldom, if ever, been in the mantle. How do we know this? How do we know what's happening down near the core? We've certainly never gotten anywhere close to the core. We would be crushed by the pressure, burned up by the temperature. No way we will ever be down there. The journey to the center of the Earth, that was mostly fiction, not much science at all there. You might say it was science fiction. No, it's mostly just fiction. Well, here's our data sources. Ha! Here is where it comes into play. The seismological data that we get from the seismic waves. We use that to interpret this. We'll see how later. This one seems to me way wild. The nature of meteorites, those are the things that are floating around in space. The Earth gets in their path. It hits our atmosphere, it comes through our atmosphere, most of them burn up, the remains that left, and they land on the Earth. Their nature tell us something about the mantle? Well, that's because they were leftover materials from what you had when the Earth was being formed. When the sun was still a protostar becoming a star, the planets were still that accretion disk, hadn't quite settled. The things that were left over were the meteorites. What things now are meteorites, so that's a pretty good indication that's what's inside the Earth. Okay, that's a stretch in my mind, but we'll go with it. The third, materials ejected from volcanoes. Some of these volcanoes, the materials are coming from way deep in the Earth into the mantle, and when we study what comes out of the volcanoes, that's a pretty good idea of what's inside the mantle. Okay, now there's also a basalt correlation. and this goes back to these meteorites. The basalt correlation of the oceanic crust and some of the top part of the mantle, those are your basalts there. They're close in silicate composition to those stony meteorites that landed from outer space. Now, the basalts are your most common volcanic rock, but that to me has not much to do with the mantle's makeup, except that it's high in iron content. Of course it is. Most of the interior of the earth is very high in iron content. Okay, so that's not surprising. Why? What makes them basalts are the fact they're molten here, right? Coming up through that, that's what volcanoes, materials ejected, they were volcanoes. Now, time out. Volcanoes throw out solid pieces as well as magma, okay, and lava. Some of the things that come out are solids, the rocks that have been picked up. Those are the ones close in chemical composition to the stony meteorites. Not the lava when it's hardened. That's what makes basalts, okay? So the most common volcanic rock is basalts. That's when the lava hardens, the magma hardens. But because it hardens quickly, it makes small particle size, small crystal size, which makes it a very fine-grained igneous rock, okay? But those chunks of rock that come out, those were probably rocks from the mantle. And when they studied those, they found out they're very similar to the stony meteorites that land on the Earth, which means that's probably what was first the Earth was predominantly made of. 80% of its volume is still there. 2/3 or 67% of its mass is still that. Okay, there's the mantle. Now we get into the core. Now, excuse me, I've got to sneeze again. Sorry. Okay, sorry about that. I hope you're awake now. All right. Let's talk about the core a little bit. Now, I did skip over something here. Let's pick it up. One was a table 18.1, comparison of the oceanic crust to the continental crust. And let's talk about that. Okay, here's the table to which I am referring, if I can get it to show up. There it is. There's the table. And with the bin in the book, that's going to be hard to read. Okay, there it is. It's up the top of page 18.4 if you're in the little skinny books, or 461 if you're in the big book. Okay, now comparison of the oceanic crust to the continental crust. First, in age, the oceanic crust typically is less than 200 million years old. That sounds pretty old, but the continental crust up to 3.8 billion years old. Now that same 3.8 billion we had from when we're talking about the moon's formation. That's when the moon basically became sort of a solid sphere. That's when the Earth cooled enough to be a solid sphere. Sun was formed about 5 billion years ago. It took another 1.2 billion years for the planets to cool off and settle in, and the moon as well, and become solid on the surface anyway. Okay, so oceanic crust less than 200 million years. That means volcanic activity since the founding of the Earth. Okay, continental crust, that was pretty much from the beginning. Okay, thickness. The oceanic crust, 3 to 5 miles thick. When I said a few miles, 3 to 5 miles, the oceanic thick. And that's the thin one. The continental crust, 6 to 47 miles thick. That's thick. Okay, very thick. We've never drilled down 47 miles. I don't think we've typically ever gotten 6 miles down. but these are typical. There are places where the mantle comes a little bit closer to the surface. So you see even the thickest part of oceanic crust, 5 miles, is still thinner than the thinnest part of the continental crust, 6 miles. Okay. The density. Now this one's pretty interesting. If we could do the lab that we used to do when we were on campus, we would see this. We would measure this. Oceanic crust around 3 grams per cubic centimeters, whereas the continental crust around 2.7 grams per cubic centimeter. Doesn't sound like a lot, but it's a pretty significant difference. Sorry. The composition: oceanic crust mostly basalts. The continental crust is mostly granite, some schist, which is the granite is an igneous rock. Schist and gneiss are metamorphic rocks. Okay, could have been made out of granite to begin with, but didn't have to be. Okay, so that was one thing the slideshow doesn't show. Worth a look. That was back on the crust. Then there's examples 18.1 and 2, and this is the working out of it is kind of nebulous, not really all that, but the information in it is pretty interesting. What is the height at which the oceanic crust floats in the mantle? Now, we haven't even talked about that concept yet. Assume the average oceanic crust thickness of about 7 kilometers, which would be right around 4.2 miles. And that was right in the middle, between 3 and 5 miles. 4.2 would be in the middle. 7 would be in between 5 and 8 kilometers. Okay? Now, they go through this and they talk about density ratios and all sorts of things that they haven't even begun to mention. But the point being, the height of the crust floating above the mantle comes out being about 6/10 of a kilometer, which would be about 4/10 of a mile. And then the next question is, what is the height at which the continental crust floats in the mantle? And you do the same kind of calculations, which they sort of just made up out of the air here. I mean, they're true. That would be about 6.3 kilometers as opposed to 0.6, so it's 10 times thicker. 5.7 there's two questions here. What is the height at which the continental crust floats in the mantle? That's the first one, 6.3 kilometers. And what is the difference between the height of the continental crust and the height of the oceanic crust? That ratio, well, no, the difference is about 5.7. So if you subtract the 0.6 kilometers from the 6.3, you get 5.7. Again, where they picked up these numbers and the formulas, they weren't given in the book that I remember seeing. Well, yeah, it is. The very last of the paragraph on page 461, last thing, it does give that formula. It doesn't even give it a number. It just sort of sticks it in at the end of a paragraph. Okay? And you can certainly play with it if you'd like. Okay, then the mantle, we talked about that. Now we're in the core. Now, the core makes up 15% of the Earth's volume. Okay? What was the mantle? Does anyone remember? 80% of the Earth's volume. So if the core is 15%, 80 and 15 is 95. So the crust would make up about 5% of the Earth's volume. Here it is covering the whole Earth, but it only makes up about 5% of the volume of the Earth. Okay. Now, what was the percent mass of the mantle? About 2/3 of the Earth's mass. Okay. The core makes up about 1/3 of the Earth's mass. What does that mean? That means the crust, that little bitty thin crust out there, is negligible compared to the other two. Yeah, it makes up a fraction of a percent, probably less than 1%, probably less than 0.5%, okay? Otherwise, you would see that it made up. So these are approximate numbers. Now, what we're going to say about the core, we know because of this P wave seismological data. Now we get back into, remember we talked about the seismic waves, then we left them, started talking about the composition. Now we're going back to tie them together. Okay, now remember, tell me 3 names for a P wave. Anybody? Primary wave, pressure wave, longitudinal wave. 3 different names, same wave. Okay? The P waves are refracted by the core that produce a P wave shadow zone. Now, what in the world are they meaning there? The picture will speak to it. Okay? Let's say we have an earthquake here. That could be anywhere on the surface of the earth. They just picked a place right here. It's not a very deep earthquake, but it is an earthquake. These pressure waves travel along here. Now notice how they bend some, because they start out going through thick mantle here, and then when they get into the less dense crust, they bend upward some. Okay? So you have the bending here. However, those who get into the core, where the density is much greater, they refract, meaning they bend inward here. When they're bending outward, it's because it's getting less dense. When they bend inward, that means it's getting more dense. Okay, so they bend inward, but then start bending outward again. Now, what's the reason for that? Well, there's actually 2. Number 1, the inner core is solid, so that bends the waves more than the liquid outer core does. So that's one reason. But then when they leave the inner core, the solid inner core, that's when they bend outward, because they're going from high density to low density. So they bend outward. But then when they reach the edge of the core, and remember, the core is not a nice smooth sphere like this. It's pretty ragged and jagged. But wherever it is, it goes from high density here to low density here, so the degree of bending or refraction changes. Well, what has happened here? This denser part here bends them inward, then they start bending outward. That leaves a shadow zone. That means there is a range here between 103 degrees from the epicenter of that earthquake, we'll talk about that term later, down to here, that's more than halfway around the globe. 90 degrees would be here, so it's more than halfway around the globe. All of a sudden, no more P waves. You see P waves here? You don't see them here, from 103 degrees to about 142 degrees. And then guess what? You start seeing P waves again, because that's where these have come out of the core after being compressed in the core, spreading out some. This will then do 140 degrees into 180 degrees, which is right down here, all the way around. So it gives you a zone there. Sorry, I'm having trouble talking. Okay, not much better, but it feels better. This shadow zone, no direct P waves here, direct P waves here, direct P waves here. Now, if the earthquake had been over here, the shadow zones would have been here and here, you know. So it's always between 103 and 142 degrees from the epicenter of the earthquake around the globe. But between 142 and 180, there you have P waves again. Now remember, the P waves go through solids and liquid, solids and liquid and solid, okay? But every one of these boundaries here has the capability of really bending the waves more than would normally be. Now, if they come in directly, they don't get bent much. But the more they're off at an angle, the more they get bent, okay? This characteristic, the fact that there is no direct P wave seen between 103 and 142 degrees of arc from the earthquake up here, or wherever it is, that indicates the core is there. The core is denser than the mantle, and the core has characteristics of being densest in the center and not as dense outer from that. That gives a lot of indication that indeed it's a liquid outer core followed by a solid inner core. And they do modeling with this. Try different densities and radii and things like this. The only one that produces this pattern significantly is that model, that you have a solid inner core, a liquid outer core, and then a varying density mantle, getting denser as you go but less dense as you go up. That fits the bill and gives them pretty much the dimensions of that outer core, inner core, and the mantle. So that's why we know. We've never drilled down to find out. We can't drill down to find out, okay? Just impossible, okay? Now, these data, matching them with the models, that is used to calculate the shape and the size of the core. The source of the data on the interior, this is the source of data on the interior makeup of the core. The fact that the waves act like this is indication that has to be how the core is formed and made. The amount of bending, that depends on density, so they can use that to approximate those data too. It's amazing what they can get out of just a little bit of data. Sorry. It's beginning to warm up in here. I'm going to turn the ceiling fan back on. Earlier today, I had to turn it off because this morning was actually a pretty pleasant morning. It was cooler than many of the mornings we've had, and I couldn't handle the fan then, but it's getting a little warmer now. All right, so that's part of our understanding of the core. Couldn't it be, though, that this is just a denser solid here, getting denser as you get in and then less denser as you come back out? Wouldn't that produce close to the same thing we've got here? It's possible, except for this. The S wave, anyone remember what the S stands for? One of three words. Three names for the S waves. Secondary wave, shear wave, those two start with S, and transverse wave, going in the opposite direction, 90 degrees out. The larger S wave shadow zone, that indicates something else. Because shear waves or transverse waves will not go through liquids. The fact you don't get any S waves making their way here. They have the same bending as the P waves do here, from the center of the quake to 103 degrees in any direction here. That's the same. But whereas P waves come through down here, no S waves come through. What does that tell you? That outer core has to be liquid. If it were solid, you would get S waves coming out. It's not. Okay? So when you combine that with the fact of what you saw happening with the P waves, those two together will help indicate to you what the inner makeup of the Earth is. Okay? So the larger S wave shadow zone extends beyond 103 degrees all the way to 180. That tells you the core acts like a liquid, not allowing shear wave or transverse wave propagation at all. So The core has two parts. Liquid outer core that prevent any of the S waves from making through, but the solid inner core which accounts for the P waves contraction here. That's the only model that does, so it must be a solid inner core here where the lines get closer together than they are from spread out to dense closer and from closer to more spread out. So that would indicate there needs to be a solid inner core. Okay. Now, that you get from the combination of the S wave data and the P wave data. All of this is seismic waves. And that's why it was important that we know which traveled faster, which traveled slower, which were transverse, which were longitudinal. You know, we needed to know that to recognize what the data are telling us here. All right. Any questions on that? Now, other core evidence. Now, this is basically, I would say, mostly on page 463, though a little bit of it may have been on the previous page, but I think most of it has come from there. Get back to these meteorites. Man, this guy loves them. It just seems so bizarre to me. Things that enter our atmosphere from outer space and crash on the surface of the Earth tells you something about the innermost makeup of the Earth. That seems to be a stretch, but seems to fit. The iron meteorites, mostly iron or iron nickel alloy, they thought to mimic the chemical composition of the core. Why would that be? Because they were thrown out there at the same time the core was being formed. Okay, so the stony meteorites would mimic that's in the mantle more, but the iron meteorites mimic, and that's why you have these different kind of meteorites. Some came from blow up from way inside, some from further out. Okay, another piece of core evidence, Earth's magnetic field. What's the source of any magnetic field? The movement of charges. So there has to be some movement of charges, and they call it turbulent flow within the liquid core. Okay, and this is why I keep saying it's not a smooth boundary either. That liquid inner core has jagged bits of the mantle in it, because when it's spinning around, the liquid tends to stay in place. It's just like if I were to take this glass, if you could see the liquid in it, and twist it like this, the liquid inside almost stays where it is. Only the part that's right against the edge of the glass inside, that moves with the glass a little bit. That's in the center hardly moves at all. So what you have happening there, the mantle is spinning with the Earth. It has to. It's part of the Earth, okay? But the liquid inside is getting hit by all that jagged roughness that as the mantle is spinning by. Friction knocks off electrons, and that movement of charge from that turbulent flow within the liquid core, that material, number one, must conduct electricity. Hey, it's iron that conducts electricity, so that's one thing. And the second thing is the movement of those charges create a magnetic field. Now, the meteorite and the magnetic field data are consistent with an iron core. You see, the other stuff just told you it was liquid, solid, but didn't tell you what it is. The fact that it's the iron meteorites are out there seeming to mimic what our core is, that would indicate iron. The material must conduct electricity. Well, lots of materials do, but the fact that iron is predominant, that sort of tends to make you think that core must be mostly iron. So the magnetic and meteorite data support the idea that you have a mostly iron core. And all the stuff coming up from volcanoes, mostly high iron content materials. Now, that was a kind of a gross look at the structure of the Earth. Now we're going to look at a little more detail here. All right. Now, before we said There's the ocean, there's the oceanic crust, there's the continental crust. Here is the upper part of the mantle, the lower part of the mantle, and the core. Okay? Well, there's some more detail in here. Number one, there is a separation between the upper mantle and the lower mantle, and that's called the asthenosphere. It's a thin, relatively thin, now remember in geological terms, thin can be a few miles, okay? Thin, hot, elastic, meaning it does retain its shape, but it's also semi-liquid, okay? Layer somewhere there in the upper mantle, okay? It's distinguished by a sharp decrease in seismic wave velocity. Now they're talking about seismic waves coming from here, going to there, dropping in velocity quickly because it's less dense. Okay, now that gives another name here. Asthenosphere is this semi-liquid range that's in between the upper mantle and the lower mantle. Let's go back to our former slide. Well, actually, we can use this one. Now, this doesn't show the crust as well. The crust is out here thin. Then we got the mantle. Then we got the outer core and the inner core. This, what is not being shown here, let's go back to the other one. It shows it better. Okay, this one right here. In between the outer mantle and the inner mantle, there is a thin layer here that's called the asthenosphere. Now, again, it can be several miles thick, but it's not super thick compared to all the other dimensions here. And it's semi-liquid, elastic, meaning it retains its shape, but it is liquid. And you can tell because there's a great decrease in velocity between the inner mantle and the outer mantle going through the asthenosphere. That's what this line is. There's the Mohorovičić between the crust and the outer mantle. This is the asthenosphere in between the outer, upper mantle and lower mantle. Okay, so let's go back. To this. Okay. Now, that gives us a new classification. The lithosphere. Remember, litho means rock. Okay? So this is a solid layer above that asthenosphere. Asthenosphere is, remember, semi-liquid, not solid. Solid up here, solid down here, semi-liquid here. Now again, is it nice smooth boundary here and here? No way. Really ragged and jagged and all mixed up there. But it's that layer in between. And above that, the solid part, upper mantle, and the crust, whether it's continental crust or oceanic crust, that solid part, the crust and the upper mantle, that's the lithosphere, the rock sphere. Okay? Solid layer above the asthenosphere. It includes the entire crust, the moho, that's the boundary between the crust and the mantle, and the upper mantle. That's what this is. Now, that part, the lithosphere, that's what's made up of these rigid plates. They're solid, but they're not all connected. That doesn't mean what it means. That means there are these plates in between, rigid plates. Within the plate they're solid, but between plates it's not. Okay? That's the whole essence of the theory of plate tectonics. That this lithosphere up here is made up of differing plates. Within a given plate, it's a solid, but between the plates, it's neither solid, liquid, or gas. It has cracks and crevices. It has discontinuities there. Okay, that's what makes it up. The asthenosphere is that semi-liquid layer here. These plates float, so to speak, on that layer of semi-liquid material. Underneath there, again, the lower part of the mantle, and that just stays solid. Okay? Not really changing much at all. Oh, I'm so sorry. I've got to have something else to drink. I think that's going to quite do it for me. Man, I don't know why. Well, I do know why. I was outside mowing and all sorts of, who knows how much poison ivy was thrown into the air and everything else. It's got my head all messed up. Okay. Now, that's that detailed structure here, or at least the theory that it exists this way, that makes up the basis for plate tectonics. So, that's where we begin in 1803. Okay. Now, there is a closer look, the top of page 464 where this begins, and this is on, they have an interesting title for it, seismic tomography. Okay. Basically using seismic waves, the earthquake waves made from earthquakes, to use to map out what's underneath. In today's lingo, you might say, have you ever heard of CAT scans? CAT scan, the CAT stands for computer assisted tomography. PET scans, I don't remember what the PE stands for. The T stands for tomography. It's using waves to map out something. And CAT scans and PET scans map out things inside your body without having to cut through it and see what's there. Well, this is saying we're using seismic waves to put together the picture for us of what the Earth's like underneath, without being able to go down and drill into the mantle and into the core. We couldn't do it if we tried. And if we did, we'd probably make a huge mess out of it anyway, but we can't. There's just no way. So here's the theory of plate tectonics. Okay. The individual continents shift positions on the Earth's surface. Now, this has been an idea that was out there, I would say, centuries before we even had a clue about plate tectonics. It was early called the continental drift. Someone just looked at a map of the Atlantic Ocean and the continents on either side of the Atlantic Ocean and said, look at here. It looks like South America came right out of the armpit of Africa here. And where this slopes this way, this slopes that way, you have a bulge here where the water goes in, you have a bulge here where the land goes in. You know, they look like they could fit. The eastern boundary of North America heads up from southwest to northeast, whereas of Europe and even parts of Africa here go from southwest to northeast. They look like if they were jammed together, they'd almost fit like a glove. Okay? It's even almost imaginable that Greenland could have come out of part of Hudson Bay here. I mean, it just looks, there's too many things that are so similar here of what's going on. When this was first, the original concept was continental drift. When this was first proposed, people said, are you nuts? Continents don't drift. They're continents. They're solid. They are in place. They've always been in place. How could you possibly assume they could be drifting? That's impossible. Hey, we've now, with very accurate measurements, centuries after that, have been able to determine, yep, they are getting further apart, at least in the Atlantic. They're drifting apart. So the individual continents shift positions on the Earth's surface. The patterns between the continental shapes could be fit together. Of course, there's some twisting going on here too. All were at once part of a single large landmass called Pangea. Now the Gea part here is the same root as geology, geography. That means earth, geo, earth. Pan is just like pandemic, covering the all thing. The pandemic is all over the earth. It's not in just one certain country. It's not an epidemic. It's not something that just a lot of people catch. It's people all over the places are catching. Well, this is saying throughout the earth, the entire earth, Pangea was one big continent, and that's what it was called, a single large landmass, Pangea, surrounded by a massive, massive, massive ocean. Okay? Originally, this was called continental drift. Now they call it plate tectonics because we have a lot better understanding of the how and the why this could be. Okay. Now, what's evidence of this happening? We'll look first at the Earth's magnetic field. Now, it's going to take them a while to put this together. Okay, they're going to give you little bits and pieces now, and it might not be entirely obvious how in the world all this works. But here's the fact. Igneous rocks, that's rocks that were made out of magma that harden. Okay, igneous rocks record the Earth's magnetic field direction, strength, and direction. And here's why. If you have volcanic activity happening, now, here's a couple of assumptions here, and I cannot begin to explain these assumptions. I just know they're true because they've been measured. The Earth's magnetic field over time, long periods of time, okay, has actually changed in field strength and in direction. And for the life of me, I cannot come up with any concept of how this could be true. The closest I can come is saying that, like many other things in nature, it follows sort of what we call a, what's the word for it? A sinusoidal pattern. That's one word for it. It's not the best. Periodic change, okay? And the combination of those sort of concepts here that, and again, I can't say why, but if that spinning of the charges inside the Earth, say if it is in that liquid outer core, that the spinning is such that it kind of drifts a little bit, okay, very, very, very slowly, and sometimes lines up this way and sometimes lines up this way. That would account for what we see. Now, why that would happen, I don't know, okay, I can't begin to guess, but it seems like that's happening. So what happens when you have iron materials coming up from the Earth's interior? Everything's a liquid, and it solidifies, okay? Now, if the Earth's magnetic field were very, very strong at that time, then you get magnetite pointing in the direction of the Earth's magnetic field, strongly pointing there, strong layers of magnetite. That's naturally occurring magnetic material. If, however, that volcanic eruption happened at some later or earlier time when the Earth's magnetic field wasn't as strong, you would not have as strong of magnetite poles. In fact, you may have no obvious magnetic nature to the solidifying magma. But then, if after it went through that period of no, it start getting stronger again, and you start getting stronger and stronger fields, but in the opposite direction, that would indicate you have this harmonic motion going on, that it was like this, it then went like this, it went to almost zero, went to zero, then started slightly negative, and it got stronger and stronger until it was very strong this way, continues its way around, zero again, strong again. This is exactly what they've measured. The igneous rock record that the Earth's magnetic field strength and direction, the magnetite poles are locked into alignment with the Earth's field on crystallization, the stronger magnets being formed when the Earth's magnetic field was stronger, weaker or no magnetized material at other times, and then reversed in the other direction. The Earth's magnetic field, now this is amazing, has varied in strength and direction over time, 22 reversals over the past 4.5 million years. Now remember, we said the Earth has been around, kicking around since about, what do we say, 4.8 million years. So this is 300, no, I'm sorry, that was 4.8 billion years. No, 3.8 billion years. So this is just in the past 4.5 million years we have measured these reversals. If we could have cored deeper and deeper, we could have found even more. 22 reversals over 4.5 million years. That would be about one reversal every 200,000 years or so. Well, guess what, folks? We haven't been around to measure these things even a fraction of that time. Okay? So therefore, we have no way of knowing whether this is something that we measured. All we've done is measure the field strength of rocks as you go deeper and deeper, and they point in opposite directions. 22 reversals in the last 4.5 million years. Amazing. All right, so here's what is illustrated. Now, I think this is a little bit faulty indicator, but number one, you notice the magnetic north is not pointing horizontal to the Earth, it's pointing downward. That's because we live on a globe. And if we're here on the globe right here at 33 degrees 23 minutes 45 seconds, and you wanted to point toward the North Pole would be down that way. You'd have to go through the Earth to get to the North Magnetic Pole. Okay? If you point it this way, you're pointing out into space there, not toward the true magnetic field of the Earth. So that's why there's always this downward component. Okay? Now, again, they're not indicating field strength here. They're just indicating direction. A little bit, you might say. These two have 3 arrows down. These have just 2 arrows down. This has 3 up, 3 down again. Now, I guarantee you it's not going to go in that pattern. And I bet you there's layers here where you have no obvious magnetic field at all. Anywhere between where it changes from down to up, that had to be arranged somewhere in there when there was no obvious magnetic field. If there's not, my whole theory is gone. Here's another area where there must be a 0 in there somewhere. Layers of no magnetic material at all. I cannot believe, I do not believe, every layer has magnetic, and sometimes they sharply turn. Things don't happen sharply, okay? They happen gradually. So I think there are layers in there where you have no magnetic field. Because it says it's varying in strength and direction. Strength means it goes down to near 0 field. Direction means it comes out the other end, pointing in this opposite direction, and gradually increasing in strength again. And then gradually decreasing in strength until it goes to 0 and comes out gradually in the opposite direction. Now that's my interpretation. Just mine. Okay. I think we beat that one to death. Let's move. Any questions on it before we leave it? Okay. So, evidence from the Earth's magnetic field, it's changed 22 times in the last 4.5 million years. So what? Well, combine that with what we've learned in the ocean. In the ocean, we have some ridges just out there. Now, this is way, way, way underneath the surface of the ocean. And you'll find ridges under there. Okay? And these ridges happen to be coincident with submarine earthquakes that they have measured. Okay, they know they're happening. In fact, one of the earlier editions of this book came with it a DVDs or CDs one, I don't remember, it so long ago, that actually had visual camera pictures of these submarine earthquakes. And it was amazing to see that lava boiling up underneath the ocean, you know, boiling up red and then quickly turning black, boiling up red, quickly turn, because it was cooling very, very quickly way underneath the ocean where temperatures are quite low, but the lava was quite hot. It was just amazing to see that thing creep up these ridges. Okay, these oceanic ridges coincide with these submarine earthquakes. There's a rift along the crest, meaning it splits and goes one way or the other way. Rift along the crest. Large amounts of heat escape from the crest. Yeah, if you got volcanic material coming out of there and it's cooling the rocks real quickly, that means the water is warming up quite a bit very quickly. Okay, so that's how they know those are happening. The most famous of these is the Mid-Atlantic Ridge. Okay, I think this next slide shows that. There it is. Now, interestingly, the islands of Iceland are right on that Mid-Atlantic Ridge, and this is one place where the lava has come, not just broken the surface of the ocean floor, but actually broken through and formed volcanic mountains above the ocean here. And that's where Iceland comes from. And notice this Mid-Atlantic Ridge tends to be almost exactly halfway between the opposite size continents. Okay? Oh man, excuse me. Hard to breathe again. This isn't going to do much good, I don't think, but oh man, this gonna take a while to get over this weekend, I think. But it was a great weekend, beautiful weather, it was just wonderful. But this is that Mid-Atlantic Ridge. Most of this is underwater, and they have mapped it. They've gone through and taken sonar and things like this and have mapped it. Here it broke the surface, and that's where the island nation of Iceland is. These are volcanic mountains that came from that Mid-Atlantic Ridge, where they actually broke the surface. Now they indicate Cape Verde Islands here. I guess they're suggesting they're also islands on that ridge. I'm not that familiar with Cape Verde Islands, but I can look them up on a globe, as can you. Okay? Now, those are the ridges. We also find oceanic trenches. Long, deep, narrow troughs with pretty steep sides there. They always run parallel to the continental edges. Now, I'll give you a hint. You don't find them here. Not along the continental edge of North America. And I doubt if you do anywhere here on this edge. I doubt if you do anywhere on this edge. Okay, any of these edges. Maybe some, but I don't know. I'll tell you where you do find them. Over here. You have trenches, really deep trenches. I was on an ammunition ship. Our home port was inside San Francisco Bay, well inland from that. And we used to go out under the Golden Gate Bridge and come back the same way. And for those measurements of depth to the ocean floor, you would see that falling off gradually, and then boom, plummet as you hit that. And then the ocean floor came back up. That was that long, narrow trench, deep trenches, deep troughs, steep sides. Here's what's happening. If the continents are drifting apart in the middle of the Atlantic, something has to give because the Earth's not getting any bigger. So something has to be subducting under on the opposite side, and that's exactly what's happening here. And guess what that is called? Uh, if you had all the Pacific Ocean here, that's called the Ring of Fire, because that's where most of your volcanoes, many of your earthquakes are in that ring of fire there, because that's where the subduction is happening underneath the continental plates. That's why I said the oceanic plates go under the continental plates. Okay, we'll get more of that later. Okay, oceanic trenches was a little bit jumping the gun on you, but they put it here, so I wanted to talk about it. Now, here's the seafloor spreading hypothesis. This is on page 466 or 18-9. Now, how are we doing on time? Okay, almost 3 o'clock. We've been going at it for about an hour and 45 minutes. So let's go a little bit longer. Seafloor spreading hypothesis. Here's what they think. Hot molten rock moves up from the Earth's interior. Now, how far in the interior? That's hard to say. There's a real tendency to think it comes from that outer core. I don't think so, because that's way, 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 way too much mantle to go through. This is from pretty much that asthenosphere. Okay, there can be pockets above the asthenosphere, but that's where I think most of this is coming from. It emerges along that rift, that place where the plates do split. The outflow goes in both directions, creating new rocks. Anytime there's magma come up and lava comes up, spreads out, it creates new rocks. On top of the last new rocks, on top of the new rocks before that, on top of the new rocks before that, it keeps that kind of motion going. Now, what we have done, we have drilled down through those layers of rock, and you see these thin sediment layers near the ridge, okay, near the ridge, thin sediment layers, becoming thicker as you get closer to the continents. They've observed that, okay? They've observed older fossils and rocks near the continents, younger ones near the rifts. In other words, the fossils that were here have been there long time. Those up here, fairly recent fossils, okay? This all fits with that seafloor spreading hypothesis. Now, here's one representation of it. Now, this is mostly probably taken from what they call carbon-14 data. These are data that they measure the amount of carbon-14 in any organic material that's down there. Carbon-14 is a relatively rare isotope of carbon. Most carbon is carbon-12. But carbon-14 is slightly radioactive, meaning it leaves you a footprint of what its concentration is by how much radiation is being produced. It has a, geologically speaking, relatively short half-life, which in our terms would be a very long half-life, probably tens to hundreds of thousands of years. Okay, is this somebody coming in? I think it is, but I can't see who, because it's iPhone. Okay, I see it now, or at least I think that's who it is. I'm going to let iPhone in, but someone has to remind me who iPhone is. Maybe by the end of the term, mini term, I'll remember this, but right now I can't recall, and I just knocked off a really expensive pen there. Okay, ionizing pen. Who is iPhone? Okay, and Andrew Allen, right? All right, good deal. Thanks. Got your mark present. So this gets us 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. I think we're down to only 11 students now. Yeah, but someone else must have had to leave. See, I can't tell when people leave. I can tell when they come in again. People leave without indicating anything on Zoom, because Zoom has a waiting room that you have to wait in. So here's what the drilling evidence has shown. The carbon-14 data show that right along that ridge, that mid-Atlantic ridge, the fossils and other things they find trapped in that ridge are 0 to 5 million years old. Now that sounds pretty old. Nothing compared to the next outer ridge on either side of that mid-Atlantic ridge. Then you find fossils that are 5 to 23 million years old on this side and on this side. Okay, so you don't find them in the middle, that's 0 to 5 million years, you find them on the side. Outside of that, in the sort of olive green here, that's 23 to 38 million years old fossils. Okay, and then outside that, the aqua blue out here, that would be 38 to 53 million years. The kind of pinkish out here, that's 53 to 65 million years. And then for a long, broad period there from 65 to 135, of course that's 70 million years, that's longer than everything else put together. Those fossils are 65 to 135 million years old. And that takes you right up to the continents. Now, as you get closer to the continents, you have subduction of this oceanic plate underneath the continental plate. So all the stuff before that pretty much was lost, okay, because it's gone back under and melted again. Okay, so the older rock fossils are near the continents here and here. The younger ones are near the center, near the rifts. So that indicates this is happening over time, spreading, getting deeper and deeper. Now the next slide, if my memory's right, magnetic seed forward spreading evidence. Okay. The first was just seafloor spreading hypothesis. This is magnetic seafloor spreading evidence that supports those hypotheses. Remember we said the layers form, sometimes they're pointing this way, sometimes the other way, sometimes this way, sometimes the other. 22 reversals over the last 4.5 million years. Okay? Now, paleo usually means ancient, very long time ago. Magnetic patterns of magnetic strips in the ocean floor basaltic rocks. They're mostly iron rocks. If they were deposited at times of strong earth magnetic field, they would form magnetite in pretty strong forms. Weaker, they just form a little magnetite, not nearly as strong. Zero, no magnetite at all, it's all hematite. And then before that, you'd find them pointing in the opposite direction, weak, getting stronger further back you go, then getting weaker further back you go, and then going to zero again, and then showing up in the opposite direction. Okay, those patterns of magnetic strips in the ocean floor basaltic rock, identical magnetic reversal patterns on either side of the ridge. In the middle of the ridge, not much has happened because there hasn't been a reversal in the last 5 million years. It's been 4.5 million. In here, no reversal then. There was a reversal here. Oh wait, no reversal here. Was a reversal somewhere in that time frame, and that's why we know. So no changes in layers here. Out here you get one change of layer, and then another, and then another, and another as you go out. The patterns, identical magnetic reversal patterns on both sides of the ridge, and these patterns match those found elsewhere, providing age determination. So if you have a combination of your carbon-14 dating that gives you an age of the fossils with the magnetic field strength, and you find out the same pattern happening there on either side, going back about the side. Oh, here's somebody else coming in. I cannot see the name. Can anyone tell who this is coming in? I can't let them in because, well, let's see, maybe I can if I go here. Oh, Labrina's here. Okay, I should have done that to begin with. All right, let me get Labrina marked here. All right, good deal. Now that gets us up to 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. This is indicating only 12, so whoever left earlier must not have come back. Oh, it probably was Angelita, Angelina, Angelina, Lita. I think I said it right the first time. She said she was going to have to go and get the assignments for her kids. Okay, so let's minimize that. Go back. So the drilling evidence indicates the patterns that we're talking about. The magnetic field, now it's so bizarre, sometimes it advances and sometimes. The magnetic seafloor spreading evidence, they show identical patterns on both sides of the ridge. Nothing in between, but the same patterns on both sides, more patterns further out, more, and they match. The patterns match those found elsewhere, providing age determination. Again, that's probably from your carbon-14 dating. Okay, it's not a match.com, it's something else. Okay, now this slide is okay. I just don't like some of the implications in it. It makes it look like all the spreading is vertical. It's not. You have the spreading going horizontally as well. But I guess they couldn't show everything in one slide, but it's just showing that it's pushing further out, and where you did have spreading on both sides, you'll see that in the middle here you have same thing on either side here, not the same thing that's in the middle. Here maybe another reversal going here and here, and these two match up together. So that's kind of what we're dealing with on this. I wish they would have shown a little bit, and maybe it would have been tough to show a little bit more of what the actual, or what would you call it, layering, I guess would be the first way would be, because you definitely have spreading out this way. It's not all vertical. In fact, the vertical really irks me, as you may be able to tell. But the same thing is happening on either side. So blue to blue, whatever this is, tan to tan, pinkish to pinkish, you know, it's happening as you go out. Same thing on either side. And some of these reversals are the same thing on either side. The plant life is the same thing on either side. All sorts of indicators on both sides of those splits. All right. So let's look at some of the lithosphere plates and boundaries between them. This is the whole basis of plate tectonics. You have these various plates who generally stay pretty close together and stay with each other, but every now and then they have movement. Okay? So the lithosphere is broken into fairly rigid plates. Now notice the word fairly here. Not totally rigid. They do some bending and relative movement. Okay, but the plates move on the ionosphere. Okay, that's kind of what I've been saying. If I could get my voice back. Man, it hurts. Okay. The plates move on this ionosphere. Remember, it's semi-liquid. elastic, and the plates can move, and they're not moving fast. No one's claiming they move fast, okay? And no one's claimed the plates are entirely rigid. They have some give and take in them, okay? We'll see later. There are ridges and there are places where there's faults and things inside the plates, okay? Not just at the edges, but they typically move that way. And when one moves one way but others moving another way, that's where you got problems, okay? Most, not all, but most of your earthquakes, your volcanoes, and other rapid changes in the Earth's crust occur most often at the plate edges. Not totally, most often at the plate edges. We'll see that illustrated shortly. There are three plate motions: divergent plates where they move further apart, convergent plates where they crash together. Now this is extreme. They move so slowly, there's no real crashing. Divergent is where they're getting slightly more apart. Converging is where they come together and transform when they're moving in different directions. Okay, like that word transverse, in different directions. Transform motions. And boundaries. Now I hope there's no one behind that black up there. I don't see anybody. Okay. Here are the plates we saw early on, very early on. And these are approximate. Don't ever imagine these are exact. Okay. Now the way they've shown this, probably the largest plate is the Eurasian plate, and that's no surprise. Asia is the largest continent, and it's adjacent to and attached to Europe, which is one of the smaller continents, but together they make one huge plate. That is all up here, most of Asia, some Europe, and over here, very little Eurasian plate over here, but this is the Europe part of it. And they're bumping up, and by the way, their boundary, there's Iceland again, their boundary is that mid-Atlantic ridge. Okay, now here it's between Eurasian plate and North American plate. Here's North American plate and African plate. Here's African plate and South American plate. Notice half of the North American plate, not half, but a portion of it is below water, oceanic crust. Much of it is continental crust. Same thing here. This is probably oceanic crust here, continental crust over here and here. So you ought to be able to figure out what, excuse me. Oh man. What kind of boundary? I'll just leave it like that. We've only are talking about, we've mentioned them, but we haven't quite defined them yet. Now, we have stuck in here what they call the Caribbean plate. And it does involve many of the Caribbean islands, and some of those islands form these island chains, which basically is telling you their original makeup. Now, let's move on south from there. Pacific plate over here, which you would think, with the Pacific Ocean being the biggest ocean in the world, that would be the biggest plate, and it is probably pretty close to it. But you see the Nazca plate takes up part of the Pacific Ocean here. The Caribbean plate goes across both continents here. There is a tiny little plate up here called the Juan de Fuca plate. Basically, I can think of only there's just a small chain of islands here, which I can't remember the name of them now. Friday Harbor is in one of them. They may be called Juan de Fuca also. Islands. It seems like they have a slightly different name, but they are made up here between these two. Now this is a pretty active zone for us because this is kind of the start of our San Andreas Fault. It's sort of hard to say where it starts and ends, but that's part of it. The tail of Alaska here, that forms right up where the Pacific Plate goes, and then you have another boundary here between the Pacific Plate and the North American Plate, a little bit between Eurasia and Pacific. Now stuck in here is another little plate, the Filipino Plate. And this is a surprising one to me, the Indian-Australian Plate. Who would have guessed it that subcontinent India always, and it is part of Asia, but it's not part of the Asian plate. It's its own plate with the Australian Plate. Now, that includes many others. Here is a major island in, I'm pretty sure that's Indonesia. Sorry, my throat's going on me. But the Philippine Islands make up part of this plate, but there's some other border islands that make up part of it too, or it's responsible for. Now, African Plate over here, in between that is the Arabian Plate, and that's basically the Arabian Peninsula here. That almost defines everything you need to know about the Arabian Plate. Okay, here it bounds the Eurasian Plate, here the African Plate. Now this boundary down here, from ancient legends, tales, and truths, this is the Red Sea. That's actually a boundary that happens because of because of the two plates coming together. The Red Sea is if I'm not mistaken, a divergent plate, and this is where Africa is actually moving off from the Arabian Peninsula a little bit more all the time. Not a major amount, not enough to notice, but over geologic time it is significant. And this whole Indian Australian Plate here. Now again, here is the island nation of New Zealand. They happen because it's right on the border. Here's what I was trying to say before. I was trying to remember the name of the island in Indonesia. But here, part of it is over here on the Eurasian Plate, and part of it is on the Pacific Plate here. But this island here, if I'm not mistaken, is one island here. I think that has the name East and West attached with it. I was trying to remember the name of the island. It may actually, oh, here's someone coming in. Sancho. Now let's see, was Sancho here before? Let me see. I thought he was. No, he wasn't. First time here today. Okay. So we're slowly getting a pretty good quorum. We've lost one, but you are getting some others. Okay. I could go on and on. I probably shouldn't. We'll mention some of these plates later. Here again, the Pacific Plate. Here's the North American Plate. Now, I found it really strange it goes down to here. I just cannot believe that is really a boundary there. It's too straight, too fixed. I think that's sort of made up here. I don't know where it actually should be. I would almost guess along here somewhere, but somewhere there is a boundary between North American and Eurasian. I don't think it's that line right there. Okay, but between the Pacific and North American, this I believe because there is a chain of islands off the tail of Alaska called the goodness. The islands are called the Aleutian Islands, and they are along that boundary. And quite often you'll have these arc islands. Like I was saying, New Zealand is an island nation made up of that one of those boundaries. In here somewhere you have some island groupings like the New Hebrides and the goodness, I can't think of all the different names of the island chains, and then certain ones in Indonesia. Some of them in this plate, some of them on that plate. Indonesia, they're all in the same country of Indonesia, and they're spread out all over the place. We'll talk more about some of these boundaries later. I was just trying to point out some of the key issues here. Again, the Mid-Atlantic Ridge is the boundary between South American plate and the African plate over here, between North American plate and African plate there, North American and Eurasian plate here. So that's an obvious boundary. You have other ridges or rises down here, and the Antarctic plate they make look like it's humongous. It really isn't, because you see on a globe that little bit at the bottom, when you spread it out and make a two-dimensional graph, it gets way spread out. So this is way bigger looking here than it is in reality. Okay, I'll leave that like this. Now here's the one thing that's always puzzled me. There is a plate colored in down here that they do not give a name to. This one down here is the Antarctic plate, the blue one here. I understand that. What's this green one over here? There is no indication of what its name is, and it's way bigger than the Juan de Fuca plate, about the same size as Caribbean plate, and maybe they haven't done enough studies of those either, but they have named them. All right, let's move on to, if I can move on, goodness gracious. Let's look at some of the boundaries. Now they mention them back here, 3 plate motions, which also they call boundaries. Divergent plates, where plates are moving apart, convergent plates where they're coming together, and transform boundaries where they're moving in different directions, and that's what the transform stands for. So let's start with the divergent plates. Now, get you where you are now, page 467 or 18-10 on your smaller indicators here. Okay, we've been at it right around 2 hours. Let's see if we can make it till lab time and take a break then. I really need one. I mostly just need to get up and move around. I get really stiff, especially after a weekend like I've had. But I'm going to try to hang in because we only have about 22 minutes to go. So let's see if we can make it. Divergent boundaries. These are boundaries where the plates are moving apart. Occur between 2 plates moving away from each other. Not past each other, not toward each other, away from each other. The molten material from the mantle, and think of that possibly asthenosphere, rises to fill the fissure that happens when the plates spread. So you form new crusts here because that molten material is coming up, forming new crusts, new basaltic crust generally, often accompanied by volcanic activity. Sometimes it's oozing out, other times it's spewing out. The prime example of this is the Mid-Atlantic Ridge, like I said before, the classic divergent boundary goes in between South America and Africa, North America, Europe, the Mid-Atlantic Ridge. And that's what we've noted and talked about several times. That's not the only ridge. That's not the only divergent boundary, but that's one of the major ones. Okay? Now, here's what they think is happening. You have ocean on either side. this is oceanic crust on either side. Now the oceanic crust makes up part of the lithosphere. The upper part of the mantle makes up the rest of the lithosphere. This is the Mohorovicic discontinuity between the crust and the upper part of the mantle. This is the asthenosphere down here, which is the boundary between the upper mantle and the lower mantle, and this is that semi-liquid elastic layer that goes in here. And you see here the mantle comes probably as close to the surface of the earth as you can get, but most of this is underwater, okay? So it's really hard to study under there. Now notice what they indicate. This is the asthenosphere down here. That's why they labeled this. Now they've shown it way, way, way thicker than the lithosphere is here. This is just for illustrative purposes. It's not that it's really that much thicker. In fact, it's probably very much thinner. However, it could be bulging here because it has places for that magma to go. Now notice the magma is not uniform. It can have in it chunks of rock that have been partially melted away, broken away, and so some of what comes up here is chunks of rock. Other parts are liquid rock, which would be magma until it reaches the surface and then become lava once it reaches the surface here. So magma fills in the fissures and builds this way and that way. So yeah, there is some building in between, but there's also spillover this way and spillover that way, because this does come all the way to the top and spills over. And that's what makes the ridge a ridge. Okay, so that's an example of a divergent boundary. Convergent boundaries, there are actually two kinds of these. No, three kinds, okay? These occur when two plates move toward each other. Now, whereas you had new crust being formed when you diverge because new magma comes up and forms new crust. Here, old crust has to be destroyed because they come together. Something has to give here. Now, there are, as I said before, three possibilities. Two of these have subduction involved. The third one does not. And there the new old crust isn't destroyed in the same sense it is here. Here it truly is destroyed. The subduction zone is the belt where one crust goes underneath the other crust. Now a lot of time this is oceanic crust being denser and thinner going underneath continental crust. That's subduction. This what was oceanic crust here going under here now no longer is crust. It's something else here. It's no longer oceanic crust there. It's former oceanic crust. Now we'll see other things happen. The subducted material partially melts and then goes back into being mantle. No longer part of the crust. So that's why old crust is destroyed in this process when you have a subduction zone. So there's three possibilities here. You have converging continental crust with oceanic crust. That's what I've just described. Continental tends to float over the oceanic. Oceanic is subducted under. Oceanic melts and goes back into the mantle. So it's no longer oceanic crust. Okay, so you've lost some crust there. That's to make up for the gain of the crust that you had at the divergent boundaries. Now, you also can have converging oceanic plates. One oceanic plate here, another one here. For some reason, one subducts under the other. Maybe a slight density issue. I don't know. It's hard to say, but that's also converging oceanic plates. Now, when that happens, that's when you have these chains of islands, because that's all usually underneath the surface of the ocean. That's a lot of friction. That's a lot of activity going on there, earthquakes and things like this, and you have underwater volcanoes happening. And if those underwater volcanoes keep growing and break the surface, that's where you get the island arc chains. at those converging oceanic plates. You can look at a globe, look at a map, and almost see where those converging plates, approximately where they occurred. And then the last of these is converging continental plates. Well, continental plates are up here high, and when they converge, they just get higher. Hey, there's not really too much destruction of continental plates. They just grow taller, so the area, well, that's a little harder to describe. Not really destruction, so to speak, of crust. It's just it gets piled up. Okay? So let's look at each of those separately. First, the ocean continental. The lighter weight, lighter density continental plate, thicker continental plate, the thinner, more dense oceanic plate subducts under the less dense, thicker continental plate. The oceanic plate of denser basaltic material subducted under the less dense granite type material of the continental shelf. Okay, let's see if we can see a picture of it. There it is. And this is why those trenches formed. Okay, the oceanic plate subducts under the thicker continental plate here, and when that happens, it's not a smooth boundary. Remember, folks, it never is a smooth boundary. It's always rough and jagged and broken and very difficult for it to slide past each other. But when it does, a lot of heat is produced, friction is produced, and that friction is hot enough to melt probably stuff that was mantle type rock here, melting that. That's the source of some of your volcanic activity. Because if this is subducting under there, you guarantee there's breaks and fissures and cracks being formed, and this magma, anytime it has a chance, it tries to come up through that, and if it finds the opening and makes its way up and blows out the top, that's where you have chains of volcanic mountains, generally right along the fairly close to the seashore. Okay, so here are these volcanic mountains. These will be basaltic rocks going down in here. On top of the continental crust here, the magma that flows down here, and here the trench occurs. You go out of here and your depth finder shows you dropping off really quickly here, maxes here, and then the depth gets less as you go on out here. That's because that trench where the oceanic crust actually subducted under the continental crust. So it's marked by oceanic trench, deep-seated earthquakes, way down here, earthquakes. We'll talk about what it means by deep-seated later, and volcanic mountains above the places where maybe some of those earthquakes occurred. Here's the example, the convergence of the South American plate with the Nazca plate. So let's go back and see that picture. South American plate over here, the Nazca plate subducting under the South American plate. And by the way, just inland here, the Andes Mountains, they rise up huge gradient going up. Not much beaches in here. There are some beaches, but no flat beaches like you have on the Atlantic side or the Gulf of Mexico, where it drops off very, very slowly. This drops off incredibly rapidly. The Andes Mountains are really tall mountains all along the boundary here, western edge of South America. In North America, we have mountains too. The Sierra Nevadas in here. They call it the Presidential Range up here. And there's other mountains that go along here. Somewhere in here, I think, is Mount McKinley, I think it is. No, there's two mountains. One in California used to be thought to be the tallest mountain in the Western Hemisphere. They found out one was taller in Alaska. And I get their names crossed up. I believe McKinley is the largest, tallest here. It's probably a volcanic mountain, and so it may actually grow some more over time. But one of the biggest earthquakes occurred right along this boundary ever and made a tidal wave that wiped out the Pacific, the Hawaiian Islands, thousands of miles away. Okay, but this is way back. Wasn't anything recent. Okay, so those are convergent. Uh, okay, I think I jumped ahead. Yeah, this was the example of convergence of the South American plate, the continental plate over the subducted Nazca plate, oceanic plate. Okay. Ocean convergence. This is where one oceanic plate, crust, subducts under another. Why? Not really sure, except they got to go somewhere, okay? One of them subducts under the other, creating a trench and an underwater ridge created by that subduction. The ridge is usually on the side that was overrode the other one, and the trench is on the side of the one which goes under the other one. The deepest trench in the oceans, the Marianas Islands Trench, is one of these ocean plate convergence. Associated with, again, very deep-seated volcanoes that happen way underneath the surface, and those volcanic eruptions, if they ever break the surface, they form these island arcs where the melted subducted material rises up above sea level through the overriding plate. Here's the illustration of that. The oceanic plate that subducts under the other oceanic plate goes down into the magma here underneath this plate. And again, not a nice smooth boundary here. Ragged, jagged, terrible friction in here. It continues on down here. Friction, not a smooth surface like this at all. That friction ultimately melts the magma material, melts some of the crust material, what used to be crust material, and if that magma can find a crevice, a crease, and I guarantee you this kind of earthquake activities here will create cracks and crevices, and they go up. They always show these bubbles in here. I don't think they really exist, but they're here. Where they break the surface, you have underwater volcanoes all along here, but every now and then they'll rise up above the surface, keep growing. These form those island arcs that you see in the Pacific. Largely, you see a few in the Atlantic as well, mostly in the Pacific, some perhaps in the Indian Ocean as well. Okay. Deep-seated earthquakes happen here where these hang up on each other in deep-seated volcanoes or volcanoes coming from some of that melted material make the way up and form underwater volcanoes or above surface, which we call island arcs. Okay, and finally the continental plate convergence. The less dense granitic material resists subduction. They both try to go up. The colliding plate pile up and therefore produce in the deformed, thicker crust of lighter materials. And there's several examples of this. One is the Tibetan Plateau, which is the home for the Himalayan mountains. So guess what, team? The Himalayas are the tallest mountains in the world, and they're getting taller because of this continental plate convergence. You got a continental lithosphere coming in here, another one coming in here. They won't subduct, so they pile up. And these make some really jagged, beautiful mountains sometimes. But these form some of the tallest mountains going. Now that can also result in some volcanic activity here where these come together like that. But quite often it's just earthquake type materials. And you'll hear earthquakes coming out of that portion of China, that portion of Nepal, those are happening periodically. The Tibetan Plateau is slowly being driven upward by that continental plate convergence. The Himalayan mountains are the results of the greatest of those changes. They are the tallest mountains in the world, still growing. Our old Appalachians here on the eastern coast of the U.S., they once were the tallest mountains, some people believe, in the planet. They have not growing any to speak of now and are actually eroding down and becoming shorter. Whereas probably the Rockies are still growing. The Andes almost definitely are still growing. Sierra Nevada is probably definitely still growing. And the Himalayas almost definitely. I mean, all of them still growing. Okay. Let's see if we can get transform boundaries done in about 4 minutes. These occur when the plates are going past each other. Now, I made it seem very rapid. They are extremely slow. Crust is not created nor destroyed when they go past each other. Okay? Irregularities in the movement along the boundaries do happen. Because if you imagine this plate trying to go this way and that one's going this way, or let's get it in the reverse direction, this one's trying to go backward, this one's trying to go forward, they get hung up on protrudences, irregularities. They just create issues there. They're trying to move, they get hung up, they can't. More pressure, finally something gives. Those sudden jerks, that's what produce earthquakes. That's nobody on the west coast, the sudden jerks. This is movement of plates. One of these is the San Andreas Fault along the California coastline, the classic example of a transform boundary. I wish they'd have shown a picture of it. I believe it's in your book. Let me see if I can get an example of it. No, I don't see it in your book. Okay, before I get too much further along, there is a blurb at the top of page 469 on measuring this plate movement. They actually now have sensitive enough material, they can measure this and find out those guys in the old days that suggest the continental drift, we have measured that continental drift. Okay? Now, what this leads to is a big question here. Okay? Present day understandings. This is on page 471. And this is very close to the very end of the chapter here. I don't think we're quite going to make it today, but we'll certainly finish this up next time. Okay, we only got 2 minutes left. Present day understandings. One major remaining question, and it's a big one. Why do the plates move anyway? What's driving them? What makes them move? Why don't they just sort of stay together and in place? And why would this happen? Now, they have several hypotheses here. One current working hypothesis is the convective cells within the asthenosphere. Convection, remember, is the movement of a fluid that could be a gas or a liquid. Here we're talking about liquids here. The hotter stuff rises because it's less dense. The cooler part goes down. You get this motion like this, sometimes called stack effect, chimney effect. This is convective cells in the asthenosphere. If you've got that turbulent flow going, that hot fluid could be rising at the diverging boundaries and moving outward and pulling those diverging boundaries further apart. Some of it escapes to form new crust, and other spreads beneath the lithosphere, dragging the overlying plates with it. Remember, the overlying plates are not smooth, slick things that it's a slide past. It pulls it. Here's the problem: little supporting evidence. No one can get down there and measure this. It's just not possible. It's way too far down. It's hot. Its instruments just would not work. Okay? So we just don't have the evidence to support it. Okay? Here is the illustration of what that's showing. Here is the convective cells. The hot mantle rock, especially um, magma, moving in sort of this direction, and over here it's moving in this direction. A little bit of it does make it through here. The rest of it, as it drags this way and this way, pulls those divergent boundaries apart. Okay? Now that's part. Others say the old plate here, old oceanic plate, and they've drawn it really, really long here, is dragging these further apart. So this is called slab. Let's see, somebody is just trying to come in. I can't see who it is. Let me go back here. Kendra is back. Okay, I think I already had her here. I'm pretty certain of it. Where are you? Come on, I know you're in here. There you are. Yeah, I already had you here. Okay. So, oh, all that looking around, I didn't let her in. Sorry about that. There we go. Let her in. All right. So, there's another hypothesis here. It could be the I've already forgotten the word now. Convective movement of the magma would be some of it comes out here and maybe pushes these a little further apart. Others part of the magma pulling on either side tends to drag them further apart. One of those is called something push, and the one down here is called slab pull. Both sort of the same ideas of the same working hypothesis. It's just which is the chicken and which is the egg. And here's the example of the heat coming from the core, going up, pushing upward, moving downward, cooling off. This is what they call the convective cells, moving in those directions there. Okay, this may be, yes, it was our last slide. And we are already over time. So before we go, I'm going to say the slideshow's over, but we're going to pick up with the top of page 471. It won't take us long, just a few minutes, to get the last thing done here. Oh, there it is. I was going to say I've lost my piece of paper. Ah, here's Labrina. She must have had to go out and come back in, but I'm pretty sure I had her here. Yep, I had her here before. Welcome back. Okay, so we'll start. It won't be in the slideshow, but it'll be on the top of page 471. Let me get my marker page in place here. And we'll talk about Harry Hammond Hess. We'll talk about another figure that's in the text. It's not on the slide set. We'll talk about geothermal energy, a nice blurb, Science and Society, and a little bit about the slab pull and whatever the other one was, some sort of push. There's two types there. So we'll wrap it up, and then we'll come back and talk about ending the chapter. So today, you want to take a quick break? Yay or nay? Anybody? Is anyone still there?
It doesn't matter.
Okay, oh, you're back. Good. I would just as soon take a quick break because I need to get up and walk some. So it will take me, I think, less than 5 minutes to come back. So what I'm going to do is pause the recording over here, and y'all please. All right. Now part of what I'm going to do here is end the recording that we were doing. I mean, end the slideshow. Oh, I forgot the headphones. Sorry about that. Sorry, I'm back, but I forgot to put on my headset. So I did start the recording back. I'm going to end the recording here. This was the last slide anyway. And what I'll do is go to a new screen share here, if I can see it on here. I think this is it here. Okay. Now this shows my Blackboard Ultra. Real pain in the neck that it is. Okay. Now I'm going to scroll down till I get to this class. Right there. Okay, there we are. Now, let me just make sure make sure nobody tried to come in while I was out, while we took our break. I know that happened once. I don't see anyone that happened to. Let's see, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. This is showing 12 people here. So we have lost a couple. Hopefully they'll be coming back. But I'm going to go to this class in Blackboard. Okay, so here I'm opening it and my Blackboard died. Okay, so I'm going to have to log back in. It only stays logged in so long. So I can't spell. My fingers are on the wrong keys. Okay. This is sort of a pain in the neck to get into, as you probably know. You can't just log in. You have to go through some other thing. Okay. Here. Okay. I'll be here. Okay. So here I've got to go back down where we were again to Physical Science 111. There, we're close, but not quite. There it is, this one right here. All right, let's see, was that him coming back? Nope, not yet. All right, now where I went, by the way, was Physical Science 111, Physical Science. Here we are at the content page, okay? Now, here's where we're heading now. I'm going to scroll down. Here are the weekly activities, and I can't get this open because you folks are in the way. Keandra, get out of the way. No, I'm just kidding. Okay, moving y'all up there so we can get to this. Okay, now I can go to the down arrow here if I can get my cursor in place. Now, there's the weeks. We're in week 4, which, by the way, is getting close to the middle of your term, of your mini term. When we finish this week, we're supposed to be halfway through the course. So we've got some ground to cover, but we're moving along pretty well now. I tried to open that. I just can't see if it's open. Yeah, here it is. Okay, I'll show you all the stuff from this week. Here's the overview and weekly to-do list. I updated this sometime recently, last night or sometime. That shows what we're doing this week. Supposedly, okay, there's a paragraph about it. We finished. We're going to do lab 4 right now, chapter 17. We started in 18.2 and 18.3. We finished those up. We did that today. We'll do lab 5 next time in the lab for chapter 18, and we will finish chapter 18 in class and begin 19. Okay, so that's not exactly in the same order, but that's what we're doing. We meet each day, blah, blah, blah. Okay. Here are the objectives. Here's the weekly to-do list. We're going to perform lab 4 now. I'll show you. I haven't put it out there yet, I don't think, but I'll put out test 4 after we finish lab today. We'll read and study 18.2. We did that today already. We'll do lab 5 the last 2 hours next time on Thursday. After we finish that lab on Thursday, I'll put this test 5 out there and then start reading on chapter 19. Do that before Thursday because that's where we'll be. So that's the week 4 overall. Here's the instructional material. This is where you'll find the lab. Okay, week 4 instructional materials. There were the PowerPoint slides. We were working on these today. We'll be starting these on Thursday. Recorded lectures, go to the YouTube video playlist link given in week 1. Instructional videos, I don't think I had any for this, but handouts, the research page instructions, the research paper instructions, locator card, and the other links given in week 1. So go there and look. Here's the lab for this lab. This is Physical Science 111, Lab 4. This is a PDF. Now I can is this someone coming back or not? Yeah, Diana is back. I didn't know she had left, but here's Diana. I'm pretty sure she was already marked present. And she's back. That's good. Okay. So here's where we'll find the lab today. Thursday's lab will be this one. Now that one's in a Word document, so that's going to be a little easier, and we'll go through how to do that. Okay, but I'm going to open this one now. Notice when I put my cursor here, it doesn't underline, even though it has an icon, so I have to come over here, click on this, and it says upload or download original file. I do that, and then while you see this happening, it's downloading. Now it's through downloading, so now I can click on the file, and there, after a while, it opens. Okay, now if my memory's right, I right click here and rotate clockwise. There we go. Properties of common minerals. Okay, I don't know if you have this yet, but if you do, you can be looking at it or you can read along on the screen here. Now, we don't have a mineral collection, or actually we do on campus, but it would be almost impossible for us to do that because we're not on campus. So we're going to do it as a computer lab. We don't have a streak plate. I didn't even have one when we were on campus, so we couldn't do that. Magnifying glass, I think I probably may have had one on campus, but we certainly couldn't use it here. Steel file, we don't have one here. I could come up with one, but we can't use it. Pocket knife, we wouldn't want to have that on campus, but if we did, we can't use it because we're not there. Copper penny, all these things, we don't have this. So here's what we're going to do. It says develop a table of mineral properties. What we're going to do is record a table of mineral properties. And what we're going to do, and they're talking about the things, and this is back from chapter 17. We had exactly these talked about, not quite in the same order, but close enough. Color, remember that's the one that's the most obvious one to see. Now, did someone just try to come in? I don't know. I can't tell because I've got too many things here. Nope, doesn't look like it. Okay. Color is the most obvious characteristic you can see when you look at a mineral. It just doesn't tell you enough information about it, and you'll see that in just a minute. Streak tells you a lot more information, but it has very few options on it. But I'll show you how to find that out. Hardness tells you a lot, and this is based on the Mohs hardness scale, which they give here. It was in the book. Here it is in your lab. Number 1, the softest mineral is considered to be talc, then gypsum, then calcite, fluorite, apatite, which is your phosphate source, feldspar, quartz, which is sand, basically sandpaper. That's why this will work on a lot of things lighter or less hard than that, including woods and things like that. Topaz, even harder. Corundum, if you really want to do something that sandpaper doesn't do well on, corundum paper is more expensive, but it will really polish just about anything, okay, except diamond. Okay, it won't get diamond because diamond's the hardest. Okay, so there's your hardness. Then we have cleavage, and cleavage and fracture basically go together. Cleavage is a tendency of a mineral to break along smooth planes. Anytime you see these minerals, those nice, pretty, smooth planes, that's because it cleaves well. Cleavage occurs in parallel planes in some minerals and in one or more directions in other minerals. Sometimes the cleavage is perfect, and other minerals may have indistinct cleavage. You can't quite tell where it is. Now, generally, if it cleaves well, now did someone just come in? I couldn't tell. Yes, there's Kendra back again. Evidently she's having trouble staying in, but I've already got her here. So here she is back. Welcome back. So cleavage and fracture go together. If a mineral cleaves really nicely, it tends not to fracture as much. If it doesn't cleave, indistinct cleavage, when you try to break it, it fractures. Minerals that do not have cleavage may show fracture in irregular broken surface rather than smooth planes of cleavage. Some minerals have distinct way of fracturing, such as in the conchoidal fracture. That would be sort of like a seashell. Obsidian would be one. Well, that's not a mineral because it doesn't have the crystal structure. It's a glass. Quartz, I'm surprised they say that is, but when it does fracture rather than come into cleaves, then it will be sort of conchoidal. I can't say that word very well. That fracture is breaking along curved surfaces like a shell, like a seashell. So these two go together, cleavage and fracture. Then luster. Luster describes the surface sheen, the way a mineral reflects light. Some of these will be things like pearly, vitreous, that's like glass, pearly like a pearl, glossy, dull. Another one will be metallic. Oh, here's one. Some will be described as metallic, and there will be some others. You'll see some of those. This, to me, is the most important mineral property, is density. That really distinguishes one mineral from another mineral. Okay? And yet, and what you're going to see, they don't include density. So we're going to put it in there. Okay? Mass per unit volume. That is a very specific measure. Now, if it's given units, then it's called density. If it doesn't have units, it's called specific gravity. That's the ratio of its density to the density of water, and in grams per cubic centimeter, which is what we usually do, that density of water is exactly 1, so the ratio, all it does is lose the units. Now, other properties, now they talk about them here, don't worry about those now. Now, we're not going to do this part B, unknown minerals, okay? But what you will do, here's results. Now, at the end of the lab, be sure you come back and fill in this blank. They have a big white space here, fill it out. Question, why is the purpose of the lab accomplished? Either yes or no. Why or why not? Give that answer. But here's the bulk of the lab. The vast majority of lab is right here. Now, some of the very things we mentioned are here, but in slightly different order. So let me show you what these are. The first page, what they list here are the minerals. Now, some of these are minerals and some of them are classes of minerals. Now, I'll explain that in just a minute. I'll explain where to go. In fact, I think I'll write it down for you now. I'm going to go to my whiteboard here and write down at least a good starting point for you. Now, I'm going to hold on just a minute here. I want to make sure I spell it correctly. It's not the spelling, it's the, here it is, right here. Yeah. Here is the front side of the lab that you're doing. I wrote on the back the best website I found to go to. Now I know that's hard to read, so I'm going to type it in here for you. Okay, I'm not going to mess with getting this right because this is the only thing I'm going to type. http:// Those are backslash or forward slashes there. Web Mineral, no S. There's another one that's webminerals.com. This one does not have the S. That's what I had to confirm. Webmineral.com slash, now you data slash, now you don't have to do this last slash, but it's a good place to get started. The first one listed on your thing is calcite. Okay. Now, I'm going to stretch this out a little bit so that makes more sense. There it is. There's the website to go to. You're not going to find them all there, but you will find most of them here at this website. Okay, that's the best place to begin. Calcite's the first mineral. There you'll have it. Okay, now hopefully you can all get there. You're used to going to websites and things like this, so let me go back to the lab. There it is, up right here. If you go to that website and find calcite, now maybe I ought to do that for you, so let me do it here. I'm going to move y'all again out of the way. Kendra, you're in the way again. There, we got it. Okay, let's do that. Let's do in the HTTP webmineral.com, remind me, slash data, right? I'm going to start with calcite, C-A-L-C-I-T-E. Hopefully that will be it. Let's see if we can go there. There it is. I don't know, did I type an E in there? I did. Dumb. Okay, that should do it. Let's do it again. Okay. Yeah. All right. Let's start here. Okay. Now, the first part here shows general calcite information, chemical formula, composition. None of that was anything we're talking about. Here's the image of calcite. This is pretty interesting. And you'll notice here several, it can be various colors and other things like this. Don't worry about this yet. Okay, that's it. Here's calcite crystallography. Again, don't worry about that here. Crystal structure. Here we go. Physical properties of calcite. Okay, now the first one that was listed on your sheet, color. There's, what is it, 5 colors there. Well, one is colorless, white, so there's your colors. Let me go back and forth to our okay, where is it now? I swear it was just here. Let's try other windows. Don't need that one. Ah, nope. Come on, it was just here. Does anyone see it? Let me see what this one is. No, that's not it. This is so aggravating. This is something that's really awkward about Zoom. That's what we're looking at here. No, it's not that one. Okay. I'm going to have to minimize this, lose it for a moment, and get mine back up. Well, oh, here comes Drew back in. He said he was leaving and coming back. He must be here. Got him here already. Okay. Um, I got you. Thanks. This is nuts. We just had it up here, and now I can't find it. It was my, oh, here it is. I was looking in the wrong place. Well, no, it's not. I just had it up, so I'm going to have to open it again. This is between Blackboard screwing up and Zoom. It's really hard to keep these straight. Okay. I want to keep this open. There, I have to go back and do this again. Okay. Okay. Now here are the table of mineral properties. Let's see if I can get, here's calcite mineral data. So the first one listed was color. There it is. If you can put all 5 of those in there, put them all 5. If you can't get but 4, do the first 4, first 3, whatever. Okay, that was the first one. Let's go back to this. The second one said luster. So it's not in the same order they were talking about before, but it's there. Let's go back here to calcite mineral data. There's luster down here. Vitreous or glassy. You can put down both words or just one, it doesn't matter. You see how you extract the information you need here. Let's go on to the next one. Streak. Okay, let's go back to calcite mineral data. There was color, blah, 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 streak, the last one here, white. You'll see that is a very common one. Okay, now, say that again. Let's see if I can. You can't read that very well. Oh, you're probably on your phone, aren't you? Okay. I don't know if I've got a zoom on here or not. I've got so many things open. But if you can get to this website, you can see all this stuff, and it's really clear to read there. Okay. I can't see a place to zoom it. Sometimes it lists one, but this one I don't see that as a possibility here. And anyone have any suggestions, I'll try it. Okay, there was streak. Okay, let's go back to this. That's the first 3 columns. Go to the next page. See, there's 19 minerals listed. The next page picks up again with calcite. This time they say hardness. So go back here to calcite mineral data. Hardness right there. Number 3, calcite. It's named after itself. Okay, so that's its hardness on the Mohs scale is number 3. Calcite is the name of that. Okay, go back to the next one. Cleavage / fracture. Okay, go here. Now you'll see cleavage is listed here. So this one cleaves very well. If you remember those crystals we saw before, they were very definitely well cleaved. Slash fracture, it is brittle. Calcite is a brittle mineral, so it will fracture, and when it does, it's concordial, just like we said before. Now you can't get all this in here, and that one little block. So put some of this. You can put those four numbers if you want to, um, uh, especially since these two are duplicating each other. Well, in fact, all three of them are duplicating. So I would just say one of these. 1011 perfect. Just put that and then slash brittle concordial. Okay? That should do it. You see, you only have a limited amount of space here. Perfect or 1011, whatever that was, perfect slash brittle concordial. That will do it. Now notice here it says other. Don't do other from the first pages. Here's what you put for other. Get this, people. What's the most important classification or property? It's density. So go back here to the calcite mineral data and look under density. There it is. Now that's actually not a density. That is specific gravity. So just put 2.71. You don't have to put it specific gravity. It's obvious that's it. That's how you fill out the thing for calcite. Okay? Now if you go back to the page, you'll see the next one here is magnetite. So how do you go to a different mineral? Okay? Well, let me see if I can do it underneath all this stuff here. There's just lots of stuff here. Okay. You could type in right here. I think you can. Okay, is someone else coming in the room? Nope, got everybody here. Okay. You could try typing in here the next one, magnetite. Let's see if we can do that. And search. All right. Are we still at the same place? I don't think so.
I think you can do like Control F.
Yeah.
To, like, index.
Okay, let's go back. Let's try it right here. Control F, is that what you said?
On mine, when I went to the website, it has like A to Z.
Yeah, that's what I'm looking for is A to Z. And I just can't see it here. And part of it is because, well, I just lost people. I don't know how I did that. I've only got Matthew left. Okay. I was looking for A to Z, and I don't see it. You said Control F gives it to you?
Yeah, so when I put the website you given to us, it took me straight to the A to Z. And like if I just choose the first letter,
Yeah.
Control F, and it takes me directly to that.
Right. See, those are the pictures of calcite. Ah, there, here it is, right here. Up it go to the top of the data set, not the bottom. And you see here A to Z. Okay, click on that and go to M for magnetite. Yeah. Oh, and then do Control F.
Yeah, and then tap in the like the letter of mineral.
Okay. Right. Or you can scroll down this way. Okay, magnetite. I'm not there yet. Still magnet. This is magnesium. Ah, here we go. Nope, not. Oh, there it is. There it is. Magnetite. Okay, and click on that. We're still in webmineral.com, and here you are back. So just keep scrolling down. Once you're in magnetite, there's the image of it. Um, there's your crystallography. We're not really, physical properties. There it is. And you can get all the things you need here for magnetite. Remember, color. I think the next one was luster. The next one was streak. The next one was hardness. The next one was cleavage slash fracture. And see, its cleavage is none. So write none, but then put slash fracture, subconcordial. So you see, you'll have some that don't cleave at all, and they only fracture. So put that.
Can you show us the properties?
Do you not see it on my screen right now?
You're zoomed in.
Say again?
Like you're zoomed in. You just keep zooming in more and more.
Well, I'm not doing anything. I mean, this is what's on my
We're
screen.
getting the whole screen. We're getting like a frame of the screen.
Okay, so are you on your phone or are you on
I'm
a
on the
computer?
PC.
You're on a PC.
It's on your end. It's not on our end.
No, I mean, okay, but I don't see a minus sign. That's what I was looking for. What do you press before you do the minus sign?
Do you have a touch screen?
No, I don't.
Never mind. Try the command button. There should be a command button.
Command button, okay. Was that the same as control button?
No, it should say command.
Is that the Windows command? And then what? What do I do next?
By the numbers, it should be to the right, and there should be like a minus sign. You know what I'm saying? And then you just press that, and it should zoom out.
Okay.
It should be on top by the numbers.
Okay. Now, when you say the numbers 1 through 0 are the F1s through F12s?
No, yeah, 1 through 0.
1 through 0. Okay. And on the right side of that, okay, there is a minus sign here, which is normally, okay.
Yeah, we'll press the command button first, then the minus sign.
Okay. No, that's giving me a searching. That's not what I want.
Hey, if you do have control minus first.
Okay, let's see. Yeah, that's what I was thinking. Control minus might be it. There's no, there is a zoom, but that's the zoom. Okay, I got to get this. I've got something up here now I don't want. Okay, and I don't think I need that either. Okay, so control minus.
Do you have a number keypad?
Yes, I do.
There's a minus sign on the number keypad.
Okay, so try that one. Okay, control minus there, and absolutely nothing happens.
Try the command and then the minus sign that's there.
Nothing happens there either. Um, but if you will go to the places I'm saying, you will see what I say. You may not be able to see it off my screen. I have a green box here in the middle that I don't know why it's here, and it has the last part of crystal structure, a warning up here, this large something, and then there's things. Is that what you're seeing? Just that part of the screen?
Yeah, we're just seeing from like.
Does it say large pop-up? Exactly. See, this green box I didn't put here. Zoom, for some reason, put it in here. And I have no way of knowing how to get rid of it. So let me see if there's just not anything. This bugs the fool out of me. This is what it's blowing up. This right in here. Uh, okay. So, so what you've got to do is do the steps I told you to do. You can't see it on my screen. I'm sorry, because this thing is in the way, and it's a thing that Zoom does, and I cannot get rid of this thing. Um, let me see. Okay, I cannot get rid of it. I can't even, let's see. I can do this a little bit. This may help a little. Does that help some? What this one says right here is cleavage. You can't see all that. This one says color. Can you see those words but not the first letter? Huh? Okay. Now that's the best I can do on this. The second entry here is color. The one next that you have is luster. Okay. Thank you. Okay, someone has his mic on. I don't think you mean to be talking, but I'm picking up a whole lot of noise. Okay, so here's color. That's the first block. Luster, I think, is number 2, and streak is number 3. That's on the first page. Then on the next page, I believe the first one is hardness, and the next one is cleavage slash fracture. Cleavage is this one on top, and for this is magnetite now. That's none. Slash fracture is subconcordial. And you don't have to do the rest of that line there. That's just a lot of extra words. So that's how you do it. And the third one says other. Other is always density. And this one right here is density. And this gives a average, it gives a range 5.1 to 5.2 with the average being 5.15. Now you can't see all that, but you could just do the range here if you wanted to. Okay, sorry I can't show any more than that because this box, I can't control it. Zoom put it here, I can't get rid of it. Okay, I don't know why it showed up here, but it does, and evidently that is blocking out everything else. Okay, yes, say again. As long as I can follow what you got, and you've got those 6 categories: color, luster, streak, hardness, then cleavage slash fracture, that's 1, and then density. The one that says other, that's density, always. Don't do anything else, density. Okay, and you'll do that for every mineral. And then to go to the next mineral, you go back up to the top of the screen here and find your A to Z again. Okay, now let's just show what the next one is. The next one is pyrite. That I believe is also a mineral, so you should be able to do that. So let's go back here and do the A to Z, and we'll pick P for pyrite. Now let's see if I can get that. I don't think I can get that in the screen because I just don't have that. But there's a thing down here. I'll show you sort of what I'm talking about here. Whoa. You see the first part of A to Z here, alphabetical listing. A index, B, C, D, E, I. Then the next one is J, K, L, M. This is, you can't see it, N, O, P. P index. Just like you see C index here, there's a P index over here off the screen. It's C index, H index, L index, P index. Click on the P, and that will get you there. Now it's alphabetical, so here you got to do a lot of doing. Pyrite's going to be right at the end of that because pyrite is PY. Oops, I would go to number 5 here, and let's see what we get. Yeah, keep going. All right, pyrite. I went, oh, there it is right there. You see it? There's pyrite. And then click pyrite. And then you'll see general pyrite information. We don't want that. You may be interested in it. There's a image of pyrite. Here's the crystallography of pyrite. We're not interested in that. Here's the physical properties of pyrite. And here they are again. And again, in order, color first, then luster, then streak, then hardness right here, then cleavage slash fracture. Okay, cleavage here, fracture here. Okay, slash, and then density right here. So you do that for every mineral. But I think you'll be far better off if you do it on your screen, on your preview. You see where you go. I'll scroll this up just a tad. No, it won't go. I can't get it up there to show it. It's webmineral.com/data, and then if you wanted to, every time type in the mineral you're looking for. Okay, does anyone have any questions on how to do this? I can't show you all of them. That's me doing the lab. You need to do the lab. But I did want to show you. Yeah, that's exactly what I wanted to do. I can't remember exactly which ones aren't, but let me go down and try. Let's just try limonite. Okay, that's going to be the one I'll try next. Okay, and let's go from here to limonite. So I'll go back up to my A to Z, click on A to Z, and y'all may have quicker ways of doing it. I'll come down here to my A to Z index, and the same line that has C index, H index, the next one over is L index. I'll click on that, and now I go down till I can find limonite. Okay, I get down to the bottom of that. I go to, you can't see it, but below here, so I'm going to go to number 2 to see if I can get limonite. So let's do page 2 here. Oh, whoa, 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 stop. Okay, I released that a long time ago. Okay, limonite. There it is. And look at what it says. See goethite. So in other words, limonite's not going to give you anything. So if you own your thing here where you see limonite, right on top, goethite. It's G-O-E, blah, 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 blah. Okay? Just like you see right here, limonite, it says see goethite. So I think you can just click on this, goethite, and there you takes you straight to goethite. And there's some interesting pictures of goethite. There's lots of really interesting things here. You can read it to your heart's content. Here you get the physical properties of goethite. Okay, so whereas limonite wasn't on webmineral.com, goethite is. Goethite is one form of limonite. Limonite is a big classification. This is a specific. So write in there goethite and then do its color, do its luster, do its streak, do its hardness next, then cleavage slash fracture, and then do its density. Always do the density in number 6. Don't just pick any other, do density. Okay, so that was one example of one that you won't find as is. So what you do, find one like it. Goethite. Quartz, I know you can find. Fluorite, I think you can. Feldspar, I think, is one that you might have difficulty with. Let's see what happens if we go to feldspar. There's a spelling of F-E-L-D-S-P-A-R. So let's go here, go back up here to our A to Z listing. Okay, and we're looking for feldspar, and scroll down a little bit till you get to feld. Okay, there you can see it on this one, the F index right there. Click on that, and let's see what happens if you go to feldspar. Whoa, not quite. Okay, here's Felbert something another, Felsamina. There is no, well, one more. Let's go down one more. You'll see there is no feldspar. You see, those are the only two FeLs that you have here. Okay, so what do you do in a case like that? In a case like that, what I would suggest is go to Google or any other search engine you want to, okay? And under Google, and again, is that same block. I don't know why it's there, okay? But here and here, I'm going to search for feldspar. Feldspar. There it is. Feldspar mineral. All right. Now, here's why you can't find it. Feldspar is the name of a large group of rock-forming silicate minerals, you can't read all this, but it's on my screen, that make up over 50% of the Earth's crust. They are found in igneous, metamorphic, and sedentary rocks. All stuff we talked about. Feldspar minerals have very similar structures, chemical composition, blah, blah, blah. Okay? So what do we do? You'll see a little bit of feldspar data on this very thing that mine took, but not enough. You can't see it here. I can't get it to you, but it does show color. It does show, it doesn't show luster. It doesn't show streak. Mohs hardness scale, it does give that. And it does do cleavage fracture. And cleavage says 2 or 3. That's pretty different from what we were seeing. Fracture along cleavage plane, so that's rather bizarre. And it does give density. But that's not what you really need, okay? You might be able to use some, but here's what I would suggest is you go on down here under feldspar, and you do see some of the information here, but not enough. So here it is, feldspar minerals education. You can use any of these places you want to. Pick the one that seems like it gives you the best information. I would suggest, now that I look at this, okay. This one right here gives albite, A-L-B-I-T-E, and northite, okay. This one here gives microcline. You can't read it on your screen, but it says sanidine, orthoclase. Now, orthoclase is one I remember our book talking about. That would be the one I would do. But whatever you do, pick it, write it down on here underneath where it said feldspar. So I was sort of leaning toward orthoclase. Let's make sure orthoclase is on there. It's not. So I would, well, first let's see if A to Z listing, if we can find orthoclase. So go back to the top and do our A to Z listing again. And this time we'll do orthoclase. Now, you won't be able to see it on the small window it gives to you, but you see B index, G index, K index, O index. That's where orthoclase will be. Now, let's see how many O's we have. You'll see some of the other names we've run across. There it is. Orthoclase right there. Or any of the other of the feldspars that you found anywhere you want to find them. I just did a Google search and I knew that we had seen orthoclase before. So let's click on that and see what we get. There it is. We're back here right there under the webmineral.com. So instead of feldspar here, just write in above that or type it in whatever, orthoclase or any of the others, albite. Okay, whatever you want to do there, do it in and then go back to orthoclase or whichever one you happen to choose and scroll down until we get to, there's the crystal, here's it is, physical properties of orthoclase. There was the color, there was the luster, there was the streak, there was hardness, there was cleavage slash fracture, and then density. So in just about all these, you can keep looking until you find something that will fit in that classification. Does that make sense? Okay. Now, I can hang with you as long as you have questions, or I know that when you're looking at mine, you can't be looking up things of your own. So you let me know if there's anything else you want me to show you. Uh, I can think of at least one more. I want to say hornblende might be one, but I bet you hornblende, um, let's just see if we can get hornblende. Um, Actually, I know of a
I have
better
one
one.
question.
Yes, what's that?
Can we turn this in on an Excel worksheet?
Can you do what?
Turn this in using an Excel worksheet?
That would be fine with me. Any way that you have the data, as long as it's all the data it's asking for here, do it. Now remember, that's that one question at the end. Do you feel like the purpose of the lab was accomplished, and why or why not? All you need is a sentence or two, and that's it. But that's also a question on the lab. Here's one I'm almost certain is not going to be found: bauxite, because that's again a classification of minerals. So let's just see if bauxite is listed. So let's go back to this one, go back to A to Z, and see if we can find bauxite. Now you might have to write things down to make sure that you have right spelling. I've run into these enough that I know them. That's under B index, and let's see what we find. It's BAUXITE, I believe it is. BAU, oh, there it is. And sure enough, no, bauxite is not listed. However, see bermite. Okay, and since it's underlined here, all you have to do is click on it. And there you go to bermite. So on the page here where it says bauxite, right over that, bermite, BOEHMITE, I believe it is. Go there, and that's what you do there. So you see, if you can't find one in the listing under webmineral.com, and you can't even find it, a listing for it, go out to Google or something like that, find what you're looking for. I think feldspar may be the only one you have to do that for. I don't know for certain, but do. But if you can find a listing for it, even if it's not this one, the one they're talking about, like uh, bermite instead of bauxite. Bauxite is a classification of aluminum ores. That's what bauxite is. So it shouldn't even be listed as a mineral. But bermite is one of those aluminum ores. So go to bermite. Write it here, and then when you go to bermite, there it is, BOEHMITE. When you go there, there is your uh, listing there. Physical properties of bermite. And again, color, luster, streak, hardness, cleavage slash fracture, density. There they are. Just about everything will have those. If you happen to pick a mineral that you don't have enough information on, pick a different one that's in that same family. Okay? But the way you're doing it here by picking the name that's in their list and clicking on it, it should give you all the information you need. All right. Now, here comes the place where I ask the question. Do you want me to stay on a bit longer just to answer questions, or do you feel like you've got enough information to go with this on your own?
I have a quick question.
Sure.
Where was the site that you were looking at for the properties?
Okay. Let's see if I can get it to show here. I don't think it'll show up here. It's webmineral.com/data slash and then whatever mineral you want to look at. Let me go back to my whiteboard. Is this the one you were asking about? http://webmineral without an S. Don't put an S on that, takes you somewhere else. .com/data, and then you can put slash and put the mineral you're looking for.
Thank you, Angelita. I think she gave it to us in the chat.
Say that again. Is this what you were looking for or asking about?
Yes, sir.
Okay, great.
She gave it to us.
Okay. All right. Now, again, like I said, I'll stay with you as long as you want me to. If you have any further questions or other things, but you think you got a good handle on how to proceed with this. And like I've heard people ask, you want me to, can I do it in Excel? Fine. Doesn't bother me any. Word? Fine. Pencil and paper? Fine. Just get me the information one way or another. You can send it to me as an attachment to an email, attachment to a Blackboard message. Any way you want to get it to me, and I'll grade it. Now, I did get started on your grading over the weekend. I did not get finished, and I certainly don't have everything out in Blackboard. I still have lots and lots of things to print, because I know people told me they were sending things to me all weekend. I was not anywhere I could print this weekend. We were out in the sticks way up in Winston County. Internet was terrible, but we didn't even have a printer there if the internet had been fine. I could sit there and grade papers, but I didn't have a lot of time for that either. So anyway, I'll try to get caught up this week as much as possible. Now, I'm losing people like flies now, so I gather from that you don't need me on here any longer. But, yes, what's the question?
I think you said earlier, like that earlier we turned in the paper is like the more bonus points you give us.
Right?
When you graded it, like the grade we have, is that with the bonus?
Yes, it is. It's with the bonus added. But remember in this course, and I don't remember who is talking to me now.
It's Matthew.
Matthew Norris?
Mm-hmm.
Okay. Remember, you're in two classes, right? One mini-term and one that's not mini-term, full term. The full term class, you could get 4 points for August, 3 points for September, 2 points for October, 1 point for November. But the mini term, there's only a couple months, so it's 2 points for August, 1 point for September. So you got the full either 2 or 4 because you turned them both in August, but you only got 2 points on the mini term one because that's the max you could get there, 4 points on the full term. Yeah, but I added them to it.
One more question.
Sure.
Was the essay, the research paper, was it 1,000 words or more?
All I suggest is you do 1 to 2 pages of text, okay? Double spaced, standard font, 12 pitch, 12 point font. No real tiny, no real big one. And I don't think it'll come anywhere close to 1,000 pages. It probably won't even, English likes you to write 5-paragraph essays. That would be way more than what I need. Now, if you get carried away and you're so interested in your subject and you want to go on, I don't take off points for it being too long. I do take points off if it's less than 1 page of text. And remember, I pointed out to you what that means. It's going to be at least 2 pieces of paper, because wherever you start typing on the first page, then it'll go down to the bottom of that page, and on the second page up to the top until you reach that same, at least that same point where you started. That's a page of text. Double space, standard fonts and margins and everything. Okay, did that answer your question? I think I've lost you. I'm down to 3 students now. Are there any other questions? Any? Do you want me to stay on or sign off?
It doesn't really matter. You can leave, I guess.
Okay, so I'm going to first stop sharing because I'm tired of sharing. Okay, so that takes us out of there. I've got Matthew and Sancho left. Okay, so unless there are further questions, I will end the recording and end the meeting for everybody. Any other questions? Se- okay, that'll be fine. That'll be great. I may not be able to print it all by Thursday, but I'll get printing as much as I can. Okay. All righty. Well, then we'll see you on Thursday then, right? Good deal. I'll end the meeting. Bye bye. Get your lab done. I'll be putting the test out there fairly soon. Not immediately, but fairly soon. All right.